Hello there, and welcome to Just About Earth, where curiosity gets cozy and the planet takes the scenic route to sleep. Tonight, we're not measuring seconds or centuries, but degrees, small numbers with vast consequences. 5 of them, to be exact. It doesn't sound like much, does it? 5 degrees. Barely a difference between reaching for a sweater or not. Between a warm day and a hot one. Between one shade of sunset and the next. But for Earth, 5 degrees has been the difference between ice and jungle, between mammoths and monkeys, between an age of frost and an age of fire. Wherever you are tonight, maybe you can feel the temperature of your own little corner of the world. Maybe it's cool where you are, the kind of evening that makes blankets feel inviting. Or maybe you're somewhere humid, where the air feels like it's already holding a conversation with the ocean. Either way, I'd love to know where you're listening from and what the weather is like right now. Because in a way, this story begins with the air around you. Every breath you take contains traces of our planet's long, warm, and occasionally feverish memory. If you find this journey soothing, if the slow unfolding of Earth's ancient tales helps you unwind or fall asleep, I'd be ever so grateful if you'd give this video a like, or maybe subscribe. It helps this calm little corner of the internet reach others who might be wide awake wondering about the same questions that drift through your mind. And I promise, tonight's story isn't meant to worry you. It's meant to show how the Earth, even in its most turbulent moments, has always found a rhythm again. So, settle in. Let your breathing slow. The world outside can wait a little while, because we're about to travel backward, not just in years or millennia, but in moods, to a time when the Earth was learning how to handle heat and discovering that even a few degrees could reshape everything that lived upon it. When you think about temperature, it's easy to imagine the numbers on a thermometer as gentle companions. 20 feels pleasant, 30 feels bright, 40 starts to whisper of extremes. But when those numbers are measured not in rooms or regions, but across an entire planet, they become something else entirely. The global average temperature is the quiet heartbeat of a world in balance. Add just a few beats too many, and that balance shifts. Oceans begin to stir differently. Winds rewrite their paths. Ice forgets its boundaries. What's astonishing is how much can change when the planet's average climbs by what would barely register on your home thermostat. In the long timeline of Earth's life, our planet has warmed and cooled many times. The continents have drifted, collided and separated again, steering the flow of currents and the breath of the atmosphere. Ice ages have come and gone like long, slow blinks, and each time the temperature has changed by just a handful of degrees, the entire face of the world has transformed. It's humbling to realise that 5 degrees of global warming once melted ice sheets larger than continents, flooded entire regions that are now dry land, and painted the poles in colours more at home in the tropics. Imagine walking outside and seeing palm trees where you'd expect pine, crocodiles basking where you'd expect penguins, and a sun that seemed to linger in a sky filled with haze instead of clouds. That's what 5 degrees once meant. It was a different kind of Earth, lush, noisy, almost restless in its abundance. But to understand how it happened, and what it felt like for the planet itself, we have to travel far beyond memory. Past history, past the first humans, even past the first forest that shaded the dinosaurs. We have to go back around 56 million years to a time scientists now call the Paleocene-Eocene thermal maximum. It's a mouthful of a name for what was, in simple terms, one of the most dramatic warmings in Earth's story. But before we reach that age, there's something comforting to remember. Earth's climate has never been static. It's a living system, constantly adjusting to balance the energy it receives from the sun with the energy it releases back into space. The oceans, atmosphere and land all participate in this long conversation. Volcanoes release gases that trap heat. Plants absorb carbon dioxide and store it. Ice reflects sunlight, keeping things cool. It's an elegant balance, one that sometimes wobbles but rarely tips over entirely. And yet, when it does, the results echo for millions of years. The last time the planet warmed by around 5 degrees, the shift wasn't instant. It took thousands of years, a slow burn compared to the blink we're experiencing now. Scientists can read that ancient story in layers of rock, in the chemistry of tiny shells buried under ocean floors, and in the fossilized forest that once brushed the edges of the Arctic. They can see when the carbon levels in the atmosphere suddenly spiked, when the oceans turned slightly more acidic, and when animals began to migrate or shrink in size to cope with the heat. The clues are everywhere, and they all whisper the same message. 5 degrees is not small when it belongs to a planet. Even now, if you listen closely to the language of climate science, you can hear a kind of quiet awe. When researchers speak of ancient warming events, they use words like abrupt, massive, and global, yet they say them softly, as if describing a memory too large to fully comprehend. That's because these changes didn't just rewrite weather patterns, they rewrote the possibilities of life. Coral reefs vanished and reappeared in new forms. Forests spread into regions that had once been tundra. Rivers rerouted themselves. Entire ecosystems reshuffled like cards in a deck. And through it all, life adapted, stumbled, evolved, and found its way again. If we look at that distant time with modern eyes, it's easy to search for lessons. What happens when the planet heats by 5 degrees? What survives? What doesn't? The answer isn't simple, but it's strangely comforting. The world didn't end. It changed, profoundly, permanently, but it endured. The creatures that roamed under that warm sky were ancestors of many that still walk, swim, or fly today. The warmth reshaped them, but it didn't erase them. It's tempting to think of 5 degrees as a number we could control, a dial we could turn up or down. But in truth, Earth's thermostat has never been that simple. It's connected to deep feedback loops, the way heat melts ice, which darkens the surface, which absorbs more sunlight, which warms the planet further, the way warming oceans release gases, which amplify the effect. Each step a whisper that becomes a murmur, then a roar. And once that roar begins, it takes a long time to quiet again. Scientists estimate that during the last Great Warming, carbon poured into the atmosphere over thousands of years from sources we still debate. Volcanic activity, methane releases, perhaps even the slow cooking of organic matter buried in seafloor sediments. The air thickened, sunlight lingered, and the world's thermostat rose by about 5 degrees Celsius. The oceans, acting as both cushion and recorder, absorbed much of that heat. In their depths, sediments began to preserve a story that would one day be read by us, 500 million years later, as we looked back and wondered what it all meant. When you picture that world, imagine something both familiar and alien. The continents were in roughly the same positions as today, but the climate zones were rearranged. There were no ice caps at the poles. Sea levels were dozens of meters higher. Forests stretched from the equator nearly to the Arctic Circle. The world was green, yes, but it was a heavy, humid green, the kind that makes you think of long summer days when the air feels too thick to move. It was a planet in slow motion, saturated, swollen with heat and life. And yet, beneath the surface, change was brewing. The oceans began to lose oxygen as warm water held less of it. Some species thrived in the new conditions, others disappeared quietly, leaving only thin lines of fossils in the rock to mark their passing. For the mammals of that time, though, this heat wave was an opportunity. They diversified, adapted, and spread into new regions, setting the evolutionary stage for the primates, and eventually us. In a strange way, we owe our existence to that ancient 5-degree fever. It's hard not to feel a flicker of connection when we realise how small a temperature shift can shape an entire era. Today, we're adding carbon to the atmosphere far faster than nature ever did back then. But the end result, a warming planet, is eerily similar. The last time Earth heated by 5 degrees, it took at least 10,000 years. Now we're approaching that mark in just a few centuries. That's the difference between a slow sigh and a gasp, between a long, meandering summer and a sudden fever. But we'll come to that later. For now, let's stay in the deep past a little longer, where time moves slowly and change feels patient. The Earth back then didn't rush. Its forests spread leaf by leaf, its seas warmed current by current, and life adapted at a pace that matched the planet's own heartbeat. There's something oddly peaceful about that. Even as the temperature rose, the world continued to turn. Clouds formed, rain fell, and the night skies glittered with familiar stars. It was still Earth, just dressed in different weather. As we settle deeper into the story, keep this in mind. The phrase 5 degrees might sound clinical, but behind it lies a saga of resilience, transformation, and rediscovery. The planet has been hot before. It has been cold. It has been both at once in different places. Each time, life found a way to keep writing the story forward. Tonight, we're going to read one of its most extraordinary chapters, so take another breath. Feel the air as it moves in and out of your lungs. That air has been here before, warmed and cooled, breathed by creatures long extinct and by forests long buried. The same molecules that drift past your window tonight once circled through a much warmer world. They've seen what 5 degrees can do, and as we follow their memory, we'll find that the last time the Earth heated by just that much, it didn't simply survive, it reinvented itself. When the world warmed for the first time after a long age of ice, it didn't happen with fanfare. There were no explosions or sudden storms, no alarm to wake the oceans from their frozen dreams. It began quietly, almost politely, as if the planet itself drew a long, deep breath after holding it for far too many centuries. And in that breath, something shifted. The balance that had kept cold locked in place began to loosen, and the slow machinery of climate turned in a new direction. For most of its history, Earth has lived in rhythm with its own breathing. Carbon moves in and out of the atmosphere like air through lungs, taken in by oceans, released by volcanoes, trapped by rocks, and freed again through time. This exchange, subtle yet relentless, is what keeps the planet's temperature in motion. It never stops completely. It just slows, pauses, and reverses. And in that long pause before the world began to warm again, the Earth was in one of its quieter moods. Ice stretched far across the poles, thick and ancient. Mountains wore glaciers like crowns, and the air carried a sharp clarity that only comes from cold. The continents were still moving, grinding, drifting as they always have. But at the time, the planet's geography allowed ice to grow. When ice grows, it brightens the Earth's face, reflecting sunlight back into space and keeping things cool. But as the millennia passed, tiny variations in the Earth's orbit, its tilt and its distance from the sun started to make subtle changes to the way sunlight touched the surface. These slow orbital cycles, called Milankovitch cycles, are like the planet's clockwork heartbeat. They don't command, but they nudge. A slightly stronger summer here, a milder winter there. Small differences that, over thousands of years, add up to an invitation for the ice to retreat. And so, the planet began to inhale warmth again. The process was slow, deliberate, almost imperceptible to any creature alive at the time. Ice melted in layers thinner than the width of a fingernail each year, but the effect built upon itself. As the white sheets retreated, they revealed darker ground and ocean beneath, which absorbed more sunlight. The Earth warmed a little more ice melted, more heat was captured. It was a feedback loop, gentle at first, then persistent, then unstoppable. The oceans, ever patient, began to store this new warmth. Water holds heat far better than air, and as the seas absorbed energy, they became the planet's great reservoirs of change. Warm water expanded, currents shifted, and the slow dance between deep and shallow layers changed tempo. What had once been a cool, oxygen-rich ocean began to grow stratified. its top layers holding heat while the depths turned sluggish. Life beneath the surface noticed first. Tiny plankton, the foundation of nearly every food web, began to change their ranges, drifting to cooler regions, leaving behind empty stretches of sea. On land, vegetation responded in kind. Where ice retreated, mosses crept in. Then came grasses, shrubs and trees. Forests began their quiet invasion, taking root in soils that had been barren for millennia. Each plant that grew drew carbon from the air, but as the world warmed, the balance shifted in unexpected ways. The more the temperature rose, the faster organic matter decayed. Bacteria and fungi worked overtime, releasing carbon dioxide back into the atmosphere faster than plants could absorb it. Nature was still talking to itself, but the conversation had changed tone. During this period, volcanoes were active in many parts of the world. They released both ash and gases, including carbon dioxide and methane. These gases thickened the atmosphere's blanket, amplifying the warming that had already begun. To an observer standing on a hillside, if such an observer existed, nothing might have seemed out of place. Seasons still came and went. Snow still fell in winter. Rain still nourished the valleys. But beneath that surface calm, the planet was quietly reconfiguring itself. The warmth spread unevenly. The poles felt it most. Near what is now the Arctic Circle, temperatures rose by more than 10 degrees. Ice sheets, which had once extended over great portions of land, melted and fed rising seas. Rivers carried this meltwater toward the oceans, changing their chemistry and their depth. In coastal regions, floodplains expanded, marshes grew and low-lying forests became lagoons. The outlines of continents blurred, shorelines wandered like restless sleepwalkers, and still the earth breathed in. There's something both reassuring and unsettling about how patient these transformations were. They remind us that the world doesn't rush, even when everything seems to be changing. From the planet's perspective, 5 degrees of warming over a few thousand years is a smooth transition, a slow reshaping, not a crisis. Species had time to migrate, to evolve, to find new homes. Coral reefs, though stressed, could shift their ranges. Forests could follow the warmth northward, seed by seed. The pace of life matched the pace of change. Yet even in that long, languid rhythm, there were moments of upheaval. When the balance between carbon stored in rocks and carbon drifting in the air tilted too far, feedback loops took over. The thawing of permafrost released methane, a gas many times more potent than carbon dioxide at trapping heat. Warm oceans, unable to hold as much dissolved carbon, began to release it back into the sky. The warmth fed itself. The cycle deepened. Imagine an orchestra slowly raising its volume over hours, so gradually that no one notices the crescendo until it's already loud. That was the world then. The melody of climate continued, familiar yet transformed, building toward a heat wave that would reshape life forever. In that warmer world, rain fell differently. The air could hold more moisture, so when storms came, they were heavier. Floods visited regions unaccustomed to them, carving new paths through valleys and plains. Elsewhere, long dry seasons settled in, turning lush grasslands into sparse scrub. Animals adapted by moving, shrinking, or evolving new ways to cope. Some mammals grew smaller, their bodies better suited to shedding heat. Others sought higher ground or cooler climates. Ecosystems rearranged themselves without any design, driven purely by survival. If you were to stand in what is now Northern Europe or North America during those days, you wouldn't find glaciers anymore. Instead, you'd see forests filled with unfamiliar species, trees that today only grow in the tropics. The air would feel thick, almost heavy with moisture, carrying scents of rich vegetation and decay. Insects would hum relentlessly, amphibians would thrive, and mammals would dart through the underbrush, already beginning to resemble the forms we know today. The seas, meanwhile, were swelling. With no polar ice to lock up water, sea levels rose tens of meters higher than today. The outlines of continents looked different. The Gulf Coast stretched farther inland. The Mediterranean spilled wider. Australia's shape was altered. Islands vanished beneath the waves, while others emerged newly born from volcanic activity. For the creatures living in those shifting environments, adaptation was not optional. It was constant. There's a quiet irony in how the same processes that gave life new opportunities also erased countless others. Coral reefs bleached and dissolved in acidifying seas. Deep ocean species perished as oxygen levels dropped. Some land animals couldn't outrun the changing climate zones. Yet at the same time, warm-blooded creatures like mammals and birds began to thrive. The heat favoured their high metabolisms. They spread, diversified, and began to dominate niches once held by reptiles. What's striking is how interconnected it all was. The warming of the air changed the chemistry of the oceans, which altered where plankton grew, which determined where fish could thrive, which affected where predators could hunt. Forests growing in new regions changed how much sunlight the planet absorbed, feeding back into temperature and rainfall patterns. Nothing happened in isolation. The Earth's systems, from clouds to currents, worked like one vast network adjusting to new inputs. And through it all, the planet seemed calm, even in its fever. No panic, no sudden breaking point, just a long inhale of heat spreading through land and sea. That's what makes studying this ancient warming so haunting. It wasn't dramatic in human terms. It was gradual, vast, and strangely quiet. And yet it remade the biosphere. Scientists studying those epochs sometimes describe it as the planet's great sigh of transition, moving from one stable climate to another. They find its traces in layers of clay, in the ratios of carbon isotopes locked within ancient shells, in the pollen grains buried beneath lake beds. Each piece of evidence tells the same story. When the Earth warms by a few degrees, it's not just the temperature that changes, it's the entire script of life. The lesson isn't that warmth is inherently bad. For many forms of life, it's been a gift. Tropical forests flourished, diversity exploded, and ecosystems bloomed in unexpected ways. But the price was upheaval, the rearranging of continents' biological furniture. Old worlds vanished to make room for new ones. As the warmth peaked, the Earth reached an equilibrium of sorts. Carbon levels stabilized. Volcanic activity subsided. Chemical reactions between rainwater and silicate rocks began to draw carbon dioxide back out of the air, slowly cooling the planet again. The great breath was complete. The world had exhaled its heat and was preparing unknowingly to inhale cold once more. That cooling would come later, but for a long while the Earth rested in its warm phase, green, humid, alive. This was the stage upon which mammals began to truly evolve into the ancestors of species that would one day read this history. It was a world of transition, yes, but also of creation. When we look back on it now, it's easy to interpret those ancient degrees as warnings, as if the past is whispering caution. But perhaps it's more accurate to hear them as reminders. The Earth has always been sensitive. Its systems respond to small nudges with large gestures. A few degrees are enough to repaint the entire planet. That's neither punishment nor miracle. It's simply how balance works on a planetary scale. So, when the world caught its breath all those millions of years ago, it was setting in motion a series of changes that would ripple forward into everything that came after. The oceans would swell and sigh, forests would spread, species would rise and vanish, the atmosphere would thicken then thin again. And eventually, from that dance of heat and time, life would find a new rhythm, one that would, in the end, lead to us. The story of that breath isn't finished, though. The warmth that followed carried its own lessons, etched not in ice or rock, but in the patterns of life that adapted to it. To understand what truly happened during that long, hot age, we have to dive deeper. Not into time, but into the chemistry of the air and sea, where the planet's real conversation with itself unfolded. Because as Earth warmed, it began to speak in the language of gases, and that dialogue, soft at first, would eventually become the pulse of an entire era. As the planet warmed and forests pressed further north, the air itself began to change in a way that few living things could notice directly. But every leaf, ocean current, and breath of wind was part of it. The warmth wasn't simply the work of sunlight or shifting orbits. It was the result of the atmosphere learning to hold onto its own heat, the way a thick blanket traps body warmth on a still night. But unlike a real blanket, this one had no edges, no seams, and no way to be folded back. The Earth was building a greenhouse without glass, and the walls were made of gas. The term we use now, greenhouse gases, sounds modern, a phrase born from laboratories and climate models. Yet the effect itself is ancient. Long before humans learned to give it a name, the planet was already fluent in it. Every eruption, every decaying leaf, every breath from an animal was part of a cycle that traded carbon between the sky, the sea, and the soil. That cycle is the reason our planet is habitable at all. Without it, Earth would be a frozen marble, hostile and barren. But when the balance tips, even slightly, the warmth doesn't stop where it should. During that ancient warming, carbon dioxide levels climbed to heights the modern atmosphere has rarely known. Today, we measure about 420 parts per million. Back then, it was closer to 2,000. To visualize that, imagine a room where invisible particles accumulate until the air itself feels thicker, heavier with heat. It wasn't poison, not in the direct sense. Animals still breathed, plants still grew, but the extra carbon changed the way the planet handled energy. Sunlight entered as always, but less of it escaped back into space. The result was subtle at first, a longer summer, a milder winter, but over centuries that gentle tilt became a transformation. Scientists can trace this rise in carbon by studying the isotopes left behind in marine sediments. Each layer is a record of the balance between organic and inorganic carbon, and during that period the signal spikes dramatically. Something had unleashed a vast pulse of carbon into the atmosphere, and though the exact trigger remains debated, the fingerprints suggest multiple culprits working together. Volcanoes may have played their part, releasing gas through fissures and vents that dotted the ocean floor. Melting permafrost could have freed trapped methane, a greenhouse gas far stronger than carbon dioxide. And then there's the possibility that warming itself destabilized methane clathrates, icy compounds on the seafloor that, once melted, released enormous volumes of gas into the water and air. Whatever the source, once the gases were free, they began to do what they always do: trap heat. A single molecule of carbon dioxide is small, but countless trillions act collectively, absorbing infrared radiation and re-emitting it, keeping warmth circulating in the lower atmosphere. It's not a violent process. It's quiet, invisible, persistent. The sky doesn't change colour, the sun doesn't burn brighter. It's more like adding an extra pane to a window. Light still gets through, but less of it leaves. Over thousands of years, that small difference reshaped oceans, weather, and life itself. The ocean, always the planet's memory keeper, felt the change first. As carbon dioxide levels rose in the air, more of it dissolved into the sea, forming carbonic acid. The chemistry of the water shifted. For many marine organisms, especially those that built shells or skeletons from calcium carbonate, this was a subtle but serious problem. Their shells began to thin. Reefs struggled to grow. Whole species of plankton changed in size and abundance, their populations moving toward cooler or less acidic waters. Because plankton form the foundation of marine food webs, their movements echoed upward, through fish, through predators, through the great whales that would one day evolve from land mammals. But the surface world was thriving in the heat. plants loved the abundance of carbon. The forests of that time grew dense and tangled, stretching across continents. In high latitudes where darkness had once ruled, lush woodlands now thrived under the round-the-clock daylight of polar summers. The trees of those regions tell a story of rapid growth and long seasons. Fossilized trunks found in what is now the Arctic Circle still bear the rings of a warm and humid climate, rings that speak of summers without frost and winters that barely cooled. Imagine standing there then, the same ground now buried under permafrost, surrounded by broad-leaved trees, dragonflies, and early primates leaping from branch to branch. The world was a greenhouse indeed, and it was alive with sound. In such warmth, rain behaved differently. The air could carry more moisture, so storms were more intense. Rivers swelled, floodplains expanded into shallow seas. Weather became less predictable, not in the chaotic sense we think of today, but in a pattern that no longer stayed still. Regions that had been dry began to see monsoons. Areas that had once been temperate felt the press of tropical heat. It wasn't a world of disasters, but of constant adjustment. The planet's system sought new balance points, new rhythms, new boundaries. What's remarkable is that despite the vastness of these changes, life continued to flourish. Evolution thrives on variation, and a warming world provides plenty of it. The mammals of that time, small, quick, and adaptable, found opportunities in the heat. Forest canopies became highways of food and shelter. New species appeared, others faded. The reptiles that had once dominated the Earth's ecosystems gave way to warm-blooded competitors who could handle the shifting climates with greater flexibility. The very conditions that might have seemed hostile to one age became the cradle for another. Still, not everything adapted in time. In the oceans, the warm, oxygen-poor layers began to suffocate some species. The balance between oxygen and temperature is delicate. Warm water holds less oxygen, and without sufficient mixing between surface and deep currents, vast zones of low oxygen, anoxic regions, began to spread. The result was not a single global die-off, but a quiet reshuffling of marine life. Some forms disappeared from the fossil record entirely. Others evolved to thrive in the new chemistry, transforming ancient ecosystems into modern prototypes. Meanwhile, on land, chemical weathering began to act as Earth's slow countermeasure. When carbon dioxide dissolves in rainwater, it forms weak acid that reacts with rocks, breaking them down and drawing carbon from the air. The process is slow but relentless, and over long periods it helps regulate climate by storing carbon in minerals. This was the planet's natural way of exhaling after its long inhale of warmth. But during the height of that ancient greenhouse, the balance between emission and removal was still uneven. Carbon remained high, and the world stayed warm. There's an image that scientists often use to describe this state. The Earth is a system in equilibrium, but at a higher energy level, like a ball resting on a hilltop instead of a valley. It's stable for a while, but one strong push could send it rolling. That was the world then, balanced, yet precariously so. The carbon cycle was working, but everything operated on the edge of excess. Even a small change in one part of the system could ripple across the entire planet. When we talk about carbon today, we tend to picture numbers and charts, parts per million and gigatons. But in that deep past, it wasn't about data. It was about the breath of the Earth itself. Each eruption, each decaying leaf, each exchange between ocean and sky was a word in the planet's ongoing conversation. Over time, that conversation grew louder, warmer, more humid. And in that warmth, the boundaries of the familiar began to blur. The Arctic wasn't white, but green. The Antarctic coast hosted forests and freshwater swamps. Creatures that would today perish in cold thrived there. Crocodiles swam in polar rivers, and turtles basked beneath canopies of fern. The difference wasn't just in temperature, but in the entire texture of life. Migration patterns shifted, evolution accelerated. The biosphere as a whole was rewriting itself to fit a new set of rules. It's tempting to imagine this world as idyllic, a paradise of abundance. In some ways it was, but it was also restless. The heat drove evaporation, which fed clouds, which in turn fed storms. Weather systems carried moisture and heat farther than before, redistributing energy unevenly. Some regions endured long droughts, others faced endless rain. The global circulation of air and water, the great conveyor belts of climate, adjusted, and in doing so they shaped everything living on the surface. The Earth doesn't have intentions, but it does have tendencies. When warmed, it tends toward feedbacks that reinforce the warmth until another force intervenes. During this ancient greenhouse phase, there was no human industry, no engines or power plants, no deforestation. The changes came from within, through the slow workings of geology and chemistry. That's what makes the event so revealing. It shows how small imbalances sustained over time can alter the entire planet's complexion. To those who study the record, the most striking realization is that the 5-degree warming we speak of wasn't distributed evenly. The poles saw far greater increases. Tropical regions changed less in absolute terms, but became unstable in other ways. New rainfall patterns, stronger storms, altered ocean currents. The planet's thermostat didn't just rise, it rewired. The great oceanic circulation known as the thermohaline current, which moves heat around the globe today, likely behaved differently then, perhaps slowing or redirecting in ways that deepened the warmth at the poles. As the centuries passed, the atmosphere reached a new equilibrium. Carbon dioxide levels stopped rising, held steady by the interplay between volcanic emissions, chemical weathering and biological uptake. For a time, the world existed in this heightened warmth, a different version of itself yet just as vibrant. The forests that covered high latitudes locked away new layers of carbon in soils and peat, a quiet foreshadowing of the coal deposits that would one day be buried, waiting for us to find them. The seas grew teeming with life, even as they changed character. Warm, stratified, sometimes oxygen-poor, they nurtured species that thrived in that exact mix of abundance and challenge. There's something fascinating about how resilient the biosphere can be. It bends, stretches and reshapes itself without ever losing its underlying vitality. When the atmosphere thickened with greenhouse gases, life didn't end, it diversified. Entire families of mammals emerged during that time. Insects evolved to match new flowering plants. Coral reefs, though different in composition, reappeared in new forms. Life took the ingredients of change and used them to write new chapters. Still, the planet's chemistry kept working behind the scenes, slowly countering the warmth. Over tens of thousands of years, rain continued to draw carbon from the air, locking it into minerals and sediments. The volcanic eruptions that had fueled the carbon surge grew less frequent. The balance began, slowly, to tilt back toward cooler conditions. But the transition wasn't quick. The Earth lingered in its greenhouse state for a long while, basking in its own exhaled warmth, content for the moment. When we look back at this period through the lens of modern understanding, it feels almost eerie. The same gases, the same processes, the same feedback loops, all still active today, just operating on a much faster timeline. The difference between then and now is speed. In the past, a rise of 5 degrees took thousands of years. Today we're tracing a similar path in centuries. The physics hasn't changed, only the tempo. But for now, in that ancient world, the pace was still gentle. The Earth continued to spin under a hazy sun-drenched sky, and life followed its rhythm. The greenhouse had no glass, only air, a transparent shield that kept the planet warm enough for the forests to grow and the seas to stay liquid. It was a world of equilibrium, delicate but enduring, and within that equilibrium, evolution was busy crafting the foundations of the age to come. As time passed and the warmth settled into the bones of the planet, another transformation began quietly in the background. the very composition of life itself started to shift, shaped by the heat, the humidity, and the changing availability of resources. The creatures of this age would become the ancestors of all modern mammals, the bearers of a legacy that would stretch forward into the human story. But for now, they were small, elusive, and utterly unaware that the stage they lived upon was still slowly heating beneath their feet. The greenhouse Earth was not a place of catastrophe. It was a place of adaptation, of momentum, of systems finding new balance. And while the planet would one day cool again, the imprint of that warmth would never fade. It would remain in the chemistry of the oceans, in the layers of rock, and in the evolution of the beings that survived it. The story of that heat, that greenhouse without glass, didn't end with stability. The warmth still had more to teach, and its lessons would be written not in the air, but in the lives of those who thrived within it. For as the atmosphere thickened and the forests spread, the next act of Earth's long drama was already beginning, the one where mammals took centre stage beneath a sun that shone just a little hotter, and the world began to hum with new kinds of life. The warmth that spread across the planet didn't arrive all at once, but there was a moment in the Earth's history when that gradual rise crossed a threshold, when the gentle incline of temperature became a climb. It happened roughly 56 million years ago, at the dawn of a new epoch, when the Paleocene gave way to the Eocene. This transition, recorded in the chemistry of rocks and the fossils of plants and animals, marks one of the most extraordinary climate events in Earth's history. Scientists call it the Paleocene-Eocene thermal maximum, or PETN for short. But that phrase, technical as it sounds, hides the strangeness and drama of what it truly was. A planetary awakening when the world, already warm, suddenly became something else entirely. If you could stand on Earth then, it wouldn't feel like a single event. You wouldn't wake up one morning to a hotter sun or see the ocean suddenly steam. But in geological terms it was swift. In less than 10,000 years, an instant by planetary standards, global temperatures rose another 5 to 8 degrees Celsius. The poles warmed even more. The deep ocean heated by several degrees, something almost unimaginable given the volume of water involved. And the carbon in the atmosphere spiked dramatically, leaving behind a signal so distinct that modern scientists can spot it like a signature in sediments around the world. No single cause has ever been agreed upon. It may have been the result of volcanic activity in what is now the North Atlantic, where immense fissures opened as continents drifted apart. Those eruptions could have baked organic rich sediments, releasing enormous amounts of carbon dioxide and methane. Or perhaps the warming triggered by that volcanic activity destabilized vast deposits of methane trapped in the deep sea, setting off a feedback loop. Once released, methane quickly oxidizes into carbon dioxide, amplifying the greenhouse effect. Whatever the exact mechanism, the outcome was unmistakable. The planet experienced a rapid, intense, and prolonged pulse of heat. The effect on the oceans was profound. As carbon dioxide levels rose, more of it dissolved into seawater, turning it acidic. This change, subtle in numbers but massive in impact, began to dissolve calcium carbonate, the substance used by many marine organisms to build shells and skeletons. Microscopic foraminifera, planktonic creatures that float near the ocean surface, began to disappear from the fossil record in huge numbers. In the deep sea, entire lineages of benthic foraminifera, which had survived for millions of years, vanished almost completely. It was one of the most significant extinctions of deep-sea life ever recorded. At the surface, however, life responded differently. Warmer waters meant faster circulation in some regions, increased productivity in others. The heat rearranged ocean currents, reshaping ecosystems. Coral reefs as we know them today were rare, but their distant predecessors adapted to the new conditions, shifting locations as they had so many times before. The oceans became both cradle and crucible, a place where change was constant and survival depended on flexibility. On land, the transformation was equally dramatic. Forests expanded toward the poles, pushing into regions that had once been cold. Fossil evidence from what is now northern Canada and Siberia shows that these areas were covered in dense subtropical vegetation. Ferns, palms, and broadleaf trees thrived in places that now lie beneath snow. The Earth's colour palette shifted toward green. Rainfall patterns followed suit. Warmer air held more moisture, leading to heavier precipitation in many regions and drought in others. Monsoons intensified. River systems expanded and shifted course. Erosion increased, carrying vast amounts of sediment into the oceans. It was as if the entire hydrological cycle had found a new tempo, faster, stronger, less predictable. And in the midst of this shifting world, mammals began to take advantage of the opportunities it presented. The Perm marks a period of explosive mammalian evolution. Many of the modern groups we recognise today, primates, horses, deer, and others, first appeared or diversified during this time. Fossil sites from this period show a remarkable increase in species variety. Animals that had once been confined to certain continents began to migrate across newly opened land bridges. With warm climates stretching from pole to pole, barriers dissolved. Ecosystems once separated by cold or arid regions became connected. The world's biosphere was, for a time, more globally unified than it had been in millions of years. There's a curious detail about the mammals of this era. They were smaller than their predecessors. Many species experienced what scientists call dwarfing. The ancestors of horses, for example, were about the size of a small dog. This miniaturization wasn't a coincidence. In a warmer world, smaller bodies are more efficient at shedding heat. Food quality may also have declined as rising carbon levels affected plant nutrition. Leaves became tougher and less rich in nutrients, forcing herbivores to eat more for the same benefit. Smaller size meant lower energy requirements. In a sense, animals were adapting not just to the temperature, but to the chemistry of the atmosphere itself. This evolutionary flexibility was one reason mammals thrived while many reptiles declined. Warm-bloodedness, the ability to regulate internal temperature, became an advantage in a world where climates varied sharply across regions and seasons. Birds, descended from the surviving lineages of dinosaurs, also benefited from this adaptability. The PTM, far from being a catastrophe in the broad sense, was a crucible of innovation. Life didn't simply endure, it diversified in response to the new conditions. For plants, the warmth and high carbon levels brought rapid growth but also new challenges. Some regions became so warm and humid that lowland forests turned into swamps. In others, drought alternated with heavy rainfall, testing the resilience of ecosystems. Pollen records from this time show waves of migration and replacement. Species that had dominated one region vanished as others took their place. The planet's biosphere was dynamic, restless, constantly reshuffling. Scientists studying this period often describe it as one of the closest analogues to our current climate trajectory. The difference, of course, is speed. The carbon that entered the atmosphere during the Perm was released over thousands of years. Today, humanity is releasing comparable amounts in a few centuries. The Earth then had time to adjust. Ecosystems migrated, adapted, and evolved alongside the changes. In our time, those same processes struggle to keep pace. The geological record doesn't just tell us what happened, it shows us how fast change can become dangerous. Still, it's important to recognise that even during the Perm, the planet didn't spin out of control. Eventually, natural processes began to draw carbon back down. Silicate weathering, the slow chemical reaction between rainwater and rock, started to lock carbon dioxide into minerals again. Marine organisms that survived continued to deposit calcium carbonate, burying carbon in sediments. Over the course of hundreds of thousands of years, the excess carbon diminished and the planet gradually cooled. The warmth faded not through catastrophe, but through chemistry and time. Yet the legacy of that heatwave endured. It reshaped evolutionary paths, altered the geography of biomes, and set the stage for everything that followed in the Eocene. The world that emerged afterward was still warm, a greenhouse Earth, but it was more stable, its extremes softened by recovery. In the fossil record, this transition looks like a boundary, a thin layer of clay separating epochs. But within that layer lies a story of transformation so profound that it redefined what Earth could be. If you could walk through that world, you might find it strangely familiar despite the alien flora and fauna. The air would feel heavy, humid, and fragrant with plant oils. Insects would be abundant, their buzzing constant. Rivers would wind through forests dense with vines and ferns. The nights would be warm, the stars shining through haze. There would be no ice anywhere, not even at the poles. The planet for a time had forgotten how to freeze, and yet beneath that lush abundance, the processes that would one day cool the Earth again were already underway. Rain fell on volcanic rock, pulling carbon from the air. Sediments accumulated in shallow seas, locking away organic matter. Over time, the system that had been thrown off balance began to steady itself. The warmth that had transformed the world became a memory written in stone, a faint trace in isotope ratios, waiting to be rediscovered millions of years later. When scientists study the PETM today, they often describe it as both a warning and a reassurance. A warning because it shows how sensitive the Earth is to carbon, and how quickly change can spread across every system. A reassurance because it demonstrates that recovery, though slow, is possible. The Earth is resilient, though not invincible. It responds always to what is placed within its atmosphere. The creatures that lived through that time knew nothing of carbon cycles or feedback loops. They experienced only the world before them, the warmth, the abundance, the shifting seasons. For them, it was normal. The idea of stability, of a normal climate, is a human invention, something we perceive because our lives are so brief. For the planet, stability is always temporary. The Earth has many states, and the PETM was one of its most extraordinary. The story of that warming isn't just about temperature, it's about the interconnectedness of everything. Volcanoes released gases, which warmed the air, which changed the oceans, which altered the course of evolution. Each element fed into the next, and long after the last eruption faded, the consequences continued to unfold. It's humbling to think that the same processes that shaped that distant world are still at work today. The physics hasn't changed, the chemistry is the same, only the context differs. We are part of a much older system, one that remembers more than we can imagine. The air we breathe has cycled through these transformations before. The difference now is that we are here to observe it, to understand it, and perhaps to influence what comes next. The Paleocene-Eocene thermal maximum was not the end of the world. It was a turning point, a brief, hot pulse in a planet's long story. When the Earth cooled again, it settled into the greenhouse climate of the early Eocene, a warm and stable period that would last for millions of years. But that stability was not silence. Beneath the calm, the planet continued to evolve, and so did life. Mammals spread into every corner of the globe, forests flourished, and oceans regained their balance. The warmth had rewritten the rules, and now those rules guided the world into its next era, an age of vibrant ecosystems and thriving species, shaped forever by a few degrees of change. And as the Earth continued to turn beneath its sun, the consequences of that ancient awakening reached even deeper, into the oceans themselves, where heat and chemistry work together in ways that would transform not just life, but the very breath of the sea. Because while the land adjusted to its new climate with forests and migrations, the oceans were engaged in their own struggle, a quiet chemical drama unfolding beneath the surface, where warmth meant not comfort, but crisis. When the air grew heavier with warmth and the forests crept toward the poles, the oceans below them were changing in ways that no creature on land could see. To the eye, they would have looked much the same. Wide, endless, blue under a soft haze, but beneath the surface they were becoming something stranger. The The same heat that nurtured life on land began to burden life in the sea. The water was growing warm, thick, and sluggish. And slowly, almost imperceptibly, the oceans began to forget how to breathe. For most of its history, the ocean has been Earth's lungs. It absorbs carbon dioxide from the atmosphere, trades gases with the sky, and circulates oxygen through its depths. That invisible exchange sustains nearly every living thing that depends on the sea. Tiny plankton use sunlight to create oxygen, just as trees do on land, and ocean currents carry that oxygen downward, feeding everything from microscopic life to whales. It's a system that seems eternal, but it depends on temperature, motion, and balance. And in a warmer world, each of those began to falter. When the planet's average temperature rose by those few crucial degrees, the heat didn't stay in the air. Water, far more efficient at storing energy, absorbed most of it. The upper layers of the ocean warmed first. Warm water, being lighter, became less willing to sink. The result was a stratified ocean, a sea divided into layers that no longer mixed easily. The top grew hot and oxygen-rich. The depths turned still and suffocating. The natural rhythm of upwelling, the slow turnover that brings cold, nutrient-rich water to the surface, began to slow. And as it slowed, so did the renewal of oxygen in the deep. This change didn't make the oceans uniformly dead. The surface remained vibrant, almost deceptively so. Plankton flourished in the warmth and sunlight, feeding fish and larger predators. But their remains, which should have drifted downward to sustain deep-sea ecosystems, often decomposed before reaching the bottom, consumed by bacteria in the low oxygen layers. Those bacteria thrived where oxygen was scarce, releasing yet more carbon dioxide and methane as they worked. It was a slow spiral, less oxygen, more decay, more gas, more heat. The fossil record shows the outcome in stark detail. In marine sediments from that era, there are dark bands rich in organic material, formed when oxygen levels dropped so low that normal decomposition halted. These black shales, as geologists call them, mark periods when vast areas of the ocean floor turned anoxic, unable to support complex life. Whole communities of benthic organisms vanished. Shell-building species so dependent on calcium and oxygen suffered most. The deep sea, once alive with burrowing creatures and delicate networks of food chains, became quiet. At the same time, the chemistry of the ocean surface was shifting. The influx of carbon dioxide from the atmosphere turned the water more acidic, dissolving calcium carbonate. Microscopic plankton that built shells, coccolithophores and foraminifera, began to change. Their shells thinned, their populations fluctuated, and in some regions they disappeared entirely. Without them, the food web lost its foundation. Coral-like organisms that relied on stable chemistry struggled to maintain their structures. The reefs of that time weren't the massive, colourful ones we know today, but they still served as nurseries for countless species. As acidity rose, many of those habitats simply melted away. And yet, even as parts of the ocean grew hostile, other regions became cradles for new life. Warm, nutrient-rich shallows fostered explosions of biodiversity. Certain species of plankton adapted to the new chemistry, evolving smaller, lighter shells, or abandoning mineralization altogether. Fish and invertebrates followed the shifting zones of oxygen, thriving where currents still mixed the waters. The seas didn't die, they changed. They became patchwork ecosystems, alternating between abundance and emptiness, each layer telling a different story. The creatures of the time would have sensed the change in their own quiet ways. Some fish began to favour shallower depths where oxygen was still plentiful. Others migrated toward cooler currents that acted as refuges. Marine reptiles, already declining since the age of the dinosaurs, found their habitats shrinking as coastlines transformed and shallow seas heated. In the deep, the silence grew thicker. The once busy mudflats of the ocean floor became barren, dotted only with traces of bacterial mats that could survive without oxygen. The atmosphere and the ocean were locked in feedback. The warmer the air became, the more carbon dioxide the oceans released. This is one of the most powerful feedback loops in nature. Normally, the ocean acts as a buffer, absorbing excess carbon, but warm water holds less gas, so when the planet heats, the sea's ability to absorb carbon declines. The excess escapes back into the air, amplifying the effect. During the Paleocene-Eocene event, this loop likely drove much of the sustained warming. Once it began, it kept feeding itself for thousands of years. The irony is that this self-reinforcing process might have started from something small, a pulse of methane from the seafloor, a series of volcanic eruptions, or the release of carbon from ancient soils. Whatever sparked it, the system responded with its own momentum. The Earth doesn't need to be forced into change, it just needs to be nudged. The oceans, vast as they are, carry the memory of those nudges for millennia. When scientists study the sediments from that time, they find chemical clues that tell the story of suffocation and recovery. Ratios of carbon isotopes reveal how quickly carbon was released and how slowly it was drawn back down. Layers of clay and black shale record alternating intervals of oxygen loss and renewal. Tiny fossils show which species survived the worst of it, and which did not. In some places, the record shows a sharp transition, a sudden drop in oxygen followed by centuries of stasis. In others, it's more gradual, suggesting that the process unfolded differently across regions. The ocean's breath wasn't cut off everywhere at once. It faded in pulses, exhaled in waves. What's remarkable is how long it took for the seas to recover. Even after the atmosphere began to cool again, the deep ocean lagged behind. Water circulates slowly on a planetary scale. A complete turnover of the global ocean can take thousands of years. That meant the low oxygen layers persisted long after surface conditions had improved. Entire ecosystems had to rebuild from the top down, repopulating the depths generation by generation. It was a slow return to balance, guided not by sudden events, but by chemistry and patience. During this time, the colour of the ocean may have looked different from today's. Warmer, plankton-rich waters tend to appear greener, reflecting the abundance of microscopic life near the surface. In some regions, the sea might have taken on a brownish hue, thick with organic matter. The air above would have carried a different scent, more earthy, tinged with sulphur from bacterial blooms. It was a living ocean, but one breathing shallowly, gasping under the weight of its own warmth. For creatures that lived along its edges, the early whales, the seabirds, the mammals venturing into coastal environments, this sea remained a source of food and danger alike. Flooded coastlines created vast new estuaries, rich in nutrients. Forests met the ocean in tangled mangrove-like systems where land animals and marine life mingled. These were productive regions, yet they were unstable. A slight shift in temperature or current could transform a lush feeding ground into a dead zone. The lesson of that time, written in stone and fossil, is that oceans are not passive backdrops to climate. They are active players. They absorb, release and redistribute energy. They hold memory. When they lose their breath, the entire planet feels it. The carbon cycle, weather systems, and even the evolution of species depend on how the ocean circulates and breathes. And in that ancient epoch, its breath had slowed almost to a halt. Still, even amid suffocation, the machinery of balance was working. Chemical weathering on land continued to pull carbon from the air. Minerals washed into the sea provided materials for shell-building organisms, allowing recovery to begin. Volcanic activity subsided. Over hundreds of thousands of years, oxygen levels slowly increased again. The black shales gave way to lighter sediments. Life crept back into the depths. First bacteria and worms, then larger creatures. The ocean's breath returned. Faint at first, then steady. What makes this history so compelling is its quietness. There was no singular catastrophe. No apocalyptic event that wiped everything clean. Instead, there was a slow suffocation followed by a slower recovery. A reminder that change on a planetary scale doesn't always announce itself with violence. Sometimes it comes with stillness, with heat, with the long pause between breaths. And yet, out of that pause came resilience. The species that survived did so by adapting to scarcity, to heat, to acid, to unpredictability. Some developed ways to tolerate low oxygen. Others changed their feeding strategies or migrated to new depths. Evolution worked quietly, one generation at a time, sculpting life that could endure the altered world. The memory of that ancient suffocation is still preserved in the chemistry of today's oceans. Modern scientists use it as a reference point, comparing it to the small but measurable oxygen declines we see now as the climate warms again. The parallels are unsettling. The processes are the same, only the speed differs. Today's oceans are warming much faster, and stratification, that layering of warm, oxygen-poor water, is happening again. It's as if the sea, after millions of years, feels the echo of its own past. But in the story of the Paleocene-Eocene oceans, there's also reassurance. The systems that failed eventually recovered. Life returned. The sea found its rhythm again. It took time, far more than any human lifespan, but balance did come back. The Earth has mechanisms for healing, though they move on scales we can barely imagine. In that long ago world, when the seas had nearly forgotten how to breathe, the land above was thriving. Forests reached their peak extent and mammals, small and nimble, began to dominate. The heat that burdened the oceans was on land an engine of diversification. The same carbon that suffocated the deep sea nourished the trees, and the same warmth that slowed ocean currents drove migration and evolution on the surface. The Earth was never entirely one thing or another, never wholly suffering or thriving, but a mix of both, always seeking a new equilibrium. And as the oceans slowly remembered how to breathe, the creatures of the land began to expand into territories that had once been uninhabitable. The planet was changing again, not back to what it had been, but forward into something new. The warmth had redrawn the boundaries of life, and now the map was being filled in once more. The sea, still deep and restless, was no longer the silent abyss it had become during its long, breathless interval. Life was returning, one cell at a time. Plankton multiplied. Coral-like organisms began to re-establish themselves. The oxygen that had once been scarce began to saturate the waters again, moving downward with each generation of mixing currents. The great ocean conveyor, slow, vast, unceasing, resumed its work. The lungs of the planet had cleared, and the next act of this long story was already taking shape above the waves, where warmth, abundance, and adaptation were about to change the very course of evolution. Because on the land that bordered those newly breathing seas, mammals were beginning to rise into dominance. The forests that blanketed the continents were filled with movement and sound. Early primates, tiny horses, and creatures that would one day define the next stage of a life on Earth. The oceans had survived their trial, and now it was the turn of the land to flourish under the same sun that had nearly stifled the sea. When the heat that had stirred the oceans finally steadied and the world settled into its long, greenhouse calm, the land above was already in motion. The forests had stretched as far as they could reach, the air was thick with moisture, and the continents were alive with small, warm-blooded creatures exploring the new possibilities of the age. The time of the great reptiles had ended millions of years earlier, leaving behind an emptiness in the hierarchy of life. Into that emptiness, quietly, confidently, came the mammals. Their rise wasn't sudden or dramatic, it was patient, gradual, like the slow spread of dawn light through mist. They had been small during the age of dinosaurs, timid and nocturnal, hiding in the shadows of creatures far larger than themselves. But the warmth and the shifting ecosystems of the new world favoured their kind. Mammals had one advantage above all others: adaptability. They could regulate their own body heat, nurse their young, and adjust to environments that fluctuated between wet and dry, hot and mild. In the Paleocene and early Eocene, those traits became the keys to success. The New World wasn't hostile. It was generous, but in unpredictable ways. And those who could adjust survived best. The forests of this age were immense and unbroken, spanning entire continents. The absence of ice at the poles meant there were no frozen barriers to movement. From what is now North America to Europe to Asia, lush canopies connected regions that had once been separated by cold or distance. The air was heavy with the scent of resin and damp soil, filled with the constant hum of insects. Vines hung from branches, ferns carpeted the ground, and rivers cut slow, winding paths through the green. It was a world built for exploration, and the mammals took full advantage. Fossil evidence shows an astonishing variety emerging during this time. Early primates appeared, small and agile, leaping through trees that grew in what is now Wyoming and Germany. Tiny horse ancestors, creatures no larger than a cat, grazed among the ferns and low shrubs. Early ungulates, the ancestors of deer, camels and cattle, began to spread. Even in the fossilized footprints left behind, scientists can see their delicate proportions and sense the speed and curiosity that defined them. With the continents closer together than they are now, migration routes were open. Animals could travel from one region to another with relative ease. The warm climate ensured that food was available year-round, and so they spread north, south, east, and west, each population evolving to suit its surroundings. The world was full of niches waiting to be filled, and evolution was busy at work. In the canopy, primates developed better vision to navigate the filtered sunlight and dense foliage. Their fingers became more dexterous, their eyes moved forward to judge distance, and their brains grew slightly larger. On the ground, hoofed mammals evolved lighter bones and longer legs, better suited for running across the soft, wet soil. Predators followed. Small carnivorous mammals with sharp teeth and keen senses, ancestors of creatures that would one day become dogs, cats, and bears. It was an age of beginnings, where every form of life seemed to be experimenting with shape and behaviour. The warmth that had burdened the oceans now served as an engine for this diversity. With so much energy circulating through the atmosphere, ecosystems became dense and productive. Plants grew faster, insects multiplied, rivers and swamps provided endless habitats. Even the poles, once barren, were home to forests teeming with birds and mammals. Fossilized wood from the Arctic Circle shows that trees once grew there as thickly as they do in modern rainforests, and the animals that lived among them felt little difference between north and south. The Earth, for a brief period, was evenly warm, its climate zones flattened. For mammals, this was opportunity on a planetary scale. Their small size and high metabolism allowed them to reproduce quickly and adapt across generations. Some grew larger, taking advantage of the abundance. Others became smaller still, finding safety in the undergrowth. Evolution was like a conversation between the planet and its inhabitants. Every environmental shift answered by a biological response. When the forests spread, animals climbed. When rivers changed course, they learned to swim. When heat thickened the air, they changed their size and behaviour to suit it. This was also the time when the ancestors of whales began their extraordinary transition from land to sea. The fossil record reveals small, hoofed mammals living near coastlines that gradually adapted to aquatic life. Their descendants would one day become the largest creatures to ever live on Earth. The path from land-dwelling scavengers to oceanic giants began in this warm world, when coastlines were rich and inviting. Warm, shallow seas offered both food and safety. Step by step, generation by generation, the mammals ventured farther into the water, trading land for ocean, lungs for new depths. The mammals that stayed on land developed their own strategies. Herbivores refined their digestive systems to process the vast variety of new plant life. Carnivores evolved sharper senses to track prey through dense forests. And in the trees, The early primates honed coordination and intelligence, navigating a world that demanded awareness, memory, and curiosity. In every environment, the warmth encouraged activity, movement, and adaptation. There's a pattern in how life responds to warmth. Diversity increases, metabolism rises, and the rate of evolution accelerates. The fossil record from this time reflects that pattern perfectly. Species appeared, spread, and sometimes vanished within spans that would seem short in geological terms. The planet wasn't static. It was restless, alive in every sense, filled with experiment and change. For scientists studying this period, one of the most striking things is the uniformity of life across continents. The mammals that roamed North America were remarkably similar to those in Europe and Asia. This wasn't coincidence, it was connection. The warm, ice-free poles allowed for easy passage between continents, and so gene flow remained constant. A creature that evolved in one region could quickly spread to another. It was, in a sense, the first truly global ecosystem since the age of the dinosaurs. But even in this thriving world, the cycles of the Earth never stopped. The same forces that had brought the warmth, volcanic outgassing, carbon buildup, and orbital variation, continued to shape the background conditions. Periods of heavier rainfall alternated with drier spells. Forests advanced and retreated. Some regions grew wetter, others began to dry. And with each slow change, new opportunities arose. The mammals followed. When lowlands flooded, they moved to higher ground. When forests thinned, they adapted to open landscapes. The ancestors of modern grazing animals began to appear, learning to live on tougher vegetation. Predators learned to run faster, to hunt in packs, or to ambush from cover. The story of the mammals was one of endless adjustment, guided not by perfection but by persistence. Their rise wasn't just biological, it changed the environment itself. As forests expanded, mammals helped shape them, eating seeds, dispersing them, trampling paths through undergrowth, maintaining a balance between growth and decay. The landscape became a living feedback system, one that sustained itself through the interaction of plant and animal. The world was alive in every direction, and mammals were now part of its rhythm rather than its afterthought. The heat that had once seemed relentless began to moderate slowly. Carbon levels in the atmosphere decreased as natural processes drew them back down. Weathering of rocks on the continents continued to lock carbon into stone, and the planet began its gradual cooling phase. But for the mammals, this change was almost invisible. The world was still warm, still generous, still filled with light and food. Their story continued unhindered, each species living out its adaptation to the moment. In places that are deserts now, there were then vast green plains. In regions that now lie frozen under ice, there were rivers and trees. The air, though heavy with moisture, was breathable and rich with scent. The hum of insects never ceased. It's likely that the nights were rarely cold, that even after the sunset, warmth lingered in the soil and the leaves. Life could continue without pause. The constant temperature made for constant activity, and the mammals used every hour of it. It's easy to think of evolution as progress, but it's better understood as response. The mammals weren't striving for a goal, they were adjusting to circumstances. Each change in the environment called for a change in form or behaviour. Those who adjusted quickly survived, and those who didn't were replaced. The fossil layers from this era are filled with traces of species that existed for only a brief geological moment. Small creatures, perfectly suited to their time, then gone when the next shift arrived. Yet through all those disappearances, the lineage continued. The pattern of life refined itself. The diversity that emerged during this age laid the foundation for nearly every modern mammalian group. Primates, rodents, bats, ungulates, and carnivores all trace their roots to this warm and fertile epoch. The balance of ecosystems, the dance between predator and prey, forest and field, took its modern form here. Every corner of the planet, from the equator to the poles, was part of this grand experiment. What made it possible was the stability that followed the chaos of the earlier warming. The temperature remained high, but steady enough for ecosystems to mature. Rainfall patterns, though variable, fell into predictable ranges. The oceans, still warm, had regained enough oxygen to support life throughout their depths. The planet was functioning again as a unified system, alive from top to bottom. For millions of years this balance held. The mammals continued their quiet conquest, populating forests, plains and coastlines. Some grew to impressive sizes. Herbivores became massive browsers, and predators evolved to match them. But the defining feature of this age wasn't size or power. It was versatility. The mammals could adapt to almost anything. That trait, once merely a survival strategy, was now the engine of their expansion. If you could walk through one of those forests, you would find it both familiar and alien. Birds would call from branches above, though not the same species that fill the air today. Small hoofed mammals would dart through the underbrush, their ears flicking at every sound. Monkeys would move overhead, their small faces alert and intelligent. The air would be dense, filled with the smell of plants and the buzz of life. Every surface would be alive with a movement: ants, beetles, frogs, and lizards. It was a living tapestry woven from millions of interactions. This age of mammals wasn't just about expansion, it was about balance. For all its warmth and abundance, the world remained delicate. The same forces that sustained life could easily tilt it into new states. And so, even as the mammals thrived, the Earth's cycles continued their slow, unhurried work. Carbon moved between air, ocean and rock. Volcanic activity flared and faded. The planet's orbit shifted slightly, changing the distribution of sunlight. These small variations were the subtle signals of change yet to come. But in this moment, the world belonged to the mammals. Their adaptability had made them the stewards of the new Earth. The forests that surrounded them, the rivers they drank from, and the skies that carried their sounds were all part of an ecosystem that had found its temporary peace. It would not last forever, nothing in nature ever does, but for millions of years it held. As the land thrived, the poles remained warm and green. The mammals didn't yet know the meaning of ice. They had no reason to fear cold, no instinct for migration toward warmth. The world they knew was stable and generous, and it shaped their biology in ways that would persist long after the warmth faded. The first true ancestors of modern species were forming, moulded by a climate that rewarded flexibility and endurance. And as they moved through the endless forests and along the quiet coasts, the Earth continued to change beneath them. The same heat that had given them opportunity was still reshaping the planet's chemistry, still driving cycles that reached from atmosphere to ocean floor. The mammals didn't notice the slow cooling beginning far away, deep in the planet's rocks and waters. They lived in the present, unaware that the era of warmth would one day end. But for now, the world was theirs. Every breath of air, every rustle in the leaves, every ripple in the water carried their story forward. The Earth had found a new balance, and life had adapted once again. The warmth that had suffocated the oceans had become the light that guided the rise of the mammals, and their march across the continents was only just beginning. The forests would grow deeper, the climates would shift, new species would rise, each one another answer to the planet's quiet, endless questions. And far to the north, where warmth had once erased the memory of ice, something remarkable was happening. A transformation of light, land and life that would make even the poles bloom. In the farthest reaches of the world, where today there is only ice, silence, and a kind of stillness that feels eternal, there was once something completely different. Long before glaciers sculpted those coasts and wind turned snow into glass, those same places were green. The poles, both north and south, were covered in forests. Trees grew where the sun now rarely rises above the horizon. Rivers flowed where the ground is now locked in frozen darkness. The world, 5 degrees warmer, had erased its boundaries between temperate and polar. The poles had forgotten they were supposed to be cold. When the Earth warms, it doesn't do so evenly. The poles always feel it most. Even small increases in global temperature spread outward and upward, magnified by feedback loops that work like echoes. Ice reflects sunlight back into space, but when that ice melts, the darker ground and ocean beneath absorb more heat. That extra warmth melts more ice, and the cycle continues. During the Great Ancient Warming, this process played out to completion. The polar ice vanished entirely. What remained was land bathed in constant summer light, a place that had never seen such abundance before. If you stood there then, you would not have seen the desolate landscapes we know today. You would have stood under a canopy of trees, their trunks tall and straight, their leaves broad and glistening. There were no tundras, no permafrost, no endless sheets of white. Instead, there were forests alive with sound, the rustle of leaves, the call of birds, the slow trickle of water over moss. The air was thick with moisture, and the soil, damp and rich, fed roots that reached deep into the ground. Even the light was different. At the poles, the sun never truly set during summer. It circled the sky in a slow, golden loop, casting long shadows and soft illumination that lasted for months. The plants had adapted to that rhythm, growing without rest. Fossilized wood tells us that these trees were not stunted or sparse. They were full forests with birch, alder, dawn redwood and even palms growing within the Arctic Circle. In what is now northern Canada, scientists have found the remains of ancient swamp cypress, the same kind that thrives today in subtropical climates. In Antarctica, long before it was a continent buried under kilometres of ice, there were ferns, flowering plants, and shallow lakes surrounded by vegetation. The world was warm from pole to pole. The temperature at the poles during that time would have been roughly 20 degrees Celsius on average, sometimes more in summer. Winters, though dark, were mild, rarely dropping below freezing. Snow fell occasionally but melted quickly. Rain was common. The constant cycle of light and water kept the forests alive year-round. In the Arctic, where the sun disappeared completely for months at a time, the plants had learned to use stored energy efficiently, relying on the long summer to fuel their dormant winter months. Life followed. The warmth brought animals to places they had never been before. Fossil evidence shows crocodiles, turtles, and other reptiles living within 10 degrees of the North Pole. They swam in slow rivers and basked on muddy banks under a sun that never set. Mammals roamed through the forests. Early primates, small herbivores, and insectivores scurrying through leaf litter. The Arctic was not a frozen frontier. It was a thriving ecosystem, busy and loud, teeming with life that found the perpetual daylight and steady temperatures ideal. This polar transformation wasn't only beautiful, it was powerful. The forests at the poles became an essential part of the planet's carbon system. Trees absorbed vast amounts of carbon dioxide, storing it in their trunks and roots. Layers of decaying leaves built up over centuries, forming thick beds of peat. When the Earth later began to cool again, much of this carbon would become trapped, buried beneath sediments, forming the first hints of what we know today as permafrost. The warmth of that age was creating the seeds of the cold that would follow. The ecosystems that flourished there were unlike anything the planet has seen since. Imagine a world where the same forest types grew from equator to pole, only changing slightly in density and character. Diversity was highest in the tropics, but even the Arctic teemed with complexity. Rivers ran full of fish, amphibians filled the wetlands, and insects swarmed the air in vast numbers. With no ice to shape the landscape, erosion worked differently. Valleys formed slowly, and floodplains spread wide. The terrain itself was soft, almost gentle, compared to the rugged topography carved later by glaciers. The way light worked at the poles added another layer of uniqueness to these forests. During the long summer, there was no night, only endless twilight, a continuous wash of pale gold. Plants adapted by using every hour of light for photosynthesis, growing at a steady, unhurried pace. When darkness came in winter, they entered a slow dormancy, conserving energy until the light returned. The animals followed suit. Some migrated south during the dark months. Others slowed their activity, relying on stored food or fat. The rhythm of life there wasn't driven by day and night, but by season and patience. To imagine these forests, it helps to think of a place that never freezes, where the word cold has lost its meaning. A place where ferns the size of a person grew beside conifers, where dragonflies as large as birds flitted through shafts of amber light, and where no creature had ever seen snow that lasted. The air was heavy with the smell of wet soil and plant resin, and the soundscape was dense. Chirps, hums, the buzz of insects, the low croak of amphibians. It was not a gentle paradise, but a rich, humid, restless world. And yet, even here, there were limits. The poles, though warm, still received less sunlight overall than the equator. The long winters, with months of darkness, forced every living thing to adapt to scarcity. Some plants dropped their leaves and waited. Some stored sugars through the bright months to survive the dark. Animals learned to migrate or hibernate. The world was warm, but it still obeyed the geometry of the planet's tilt. Balance always returns in some form. Scientists studying the fossilized soils and sediments from these regions can read the changes in astonishing detail. Layers of pollen reveal which trees grew where and how those communities shifted over time. Chemical traces in the soil show the cycling of nutrients through rain and decay. Tree rings, yes, even in those ancient trunks, reveal patterns of mild winters and long summers, the steady pulse of a planet basking in equilibrium. These clues tell us that the warmth lasted for millions of years. It was not an anomaly, it was a stable phase of Earth climate. During this period, the continents were still drifting slowly toward their modern positions. The openings and closings of seaways influenced ocean circulation, which in turn affected how heat was distributed. Warm currents reached high latitudes, delivering energy that kept the poles mild. The deep ocean, though still carrying the legacy of earlier warmth, began to circulate more efficiently, spreading oxygen and stabilizing marine life. The whole planet was functioning as a unified system, the air, land, and sea in constant dialogue. The forests at the poles played a quiet but crucial role in maintaining that balance. By covering the high latitudes in green, they changed how the Earth reflected sunlight. Dark forests absorb far more heat than bright ice or tundra. This reinforced the warmth, preventing cooling from taking hold. It was a self-sustaining state, one that would last until tectonics and chemistry together shifted the balance once more. These polar forests were also windows into evolution's flexibility. The plants growing there weren't entirely different species from those found farther south. They were variations, forms that had adapted to longer days, dimmer light, and mild but seasonal shifts. Many of the trees developed broad leaves to capture as much sunlight as possible, while others evolved thick bark to protect against the long winter darkness. Some species bore both tropical and temperate traits, as if the distinction between those zones had ceased to matter. The animals living there mirrored that adaptability. In the fossil beds of ancient Arctic riverbanks, paleontologists have found the bones of turtles, birds, and mammals, all preserved in sediments that suggest year-round habitation. These creatures didn't just visit, they lived there. That means they survived the months of darkness, finding food in a world without photosynthesis. Perhaps they scavenged fallen vegetation, or preyed upon those who didn't adapt quickly enough. The polar night wasn't empty, it was merely quieter. What these forests represent is a version of Earth that feels almost mythical to us now. A place without ice caps, where the extremes of temperature were muted and the biosphere reached its widest extent. It was a demonstration of what 5 degrees of warmth could achieve, not destruction, but transformation. The planet had reinvented its polar regions, turning wastelands into jungles. In the broader rhythm of Earth's climate, this was an extended exhale, a long release of heat and abundance. It couldn't last forever, and eventually the balance would tilt again. Over millions of years, slow geological processes would draw carbon from the air. The continents would drift farther apart, and ocean currents would rearrange themselves once more. The first hints of cooling would begin quietly, unnoticed by the creatures thriving under the endless sun. But during this era, the Earth reached a kind of harmony it had not known before. Every latitude supported life. The boundaries between ecosystems blurred. The poles were no longer distant, forbidding places, but parts of the same living network that stretched across the planet. And all of it, every leaf, every river, every rustle in those ancient woods, was the result of a few degrees of change. If you were to hold a fragment of that world today, a piece of petrified wood from an Arctic floodplain, or a leaf imprint found in Antarctic rock, it would look ordinary at first glance. But within it lies the memory of a time when warmth reached the edges of the world and stayed there. It's difficult to imagine, standing in the silence of modern ice, that the same ground once supported towering trees and restless animals. Yet it did, for millions of years, until the slow machinery of cooling began to turn again. Those forests at the poles were not a mistake or an accident. They were the Earth's way of expressing balance under warmth, proof that the planet can exist in many forms and still sustain life. And while that warmth would eventually fade, the legacy of those green poles remained imprinted in the fossils and sediments that now lie buried under ice. The memory of that time still shapes the planet today. The carbon those forests stored, the sediments they built, the minerals they weathered, all became part of the long, slow cycles that govern Earth's climate. The forests at the poles were not simply the result of warming. They became part of how the Earth would one day cool again, and as the warmth began its long retreat and the air grew ever so slightly less heavy, the world above those ancient canopies began to change once more. The skies that had once poured steady rain started to shift. Storms grew wilder, winds stronger, and patterns less predictable. The forests would endure for a time, but the next transformation was already beginning. Not from heat alone, but from the restless energy that heat unleashed in the air itself. The air that had once moved softly across a warm and stable planet began to stir differently. The gentle, predictable circulation that had cradled forests from equator to pole became restless. The same warmth that had spread life's abundance now filled the atmosphere with energy, and that energy had to go somewhere. The winds grew more assertive, rain fell harder, the skies that had been mild and luminous learned again how to roar. The planet's weather, long drowsy under steady sunlight, began to move toward chaos. In a greenhouse world, every molecule of air carries more potential. Warm air holds more moisture, and with that comes a simple truth. The more water the sky can hold, the more it can release. Storms became larger, heavier, and more persistent. Rivers that had once followed lazy courses began to flood their banks. Entire regions alternated between drought and deluge. The world had not become hostile, but it had become unpredictable. To the creatures living within it, this shift was not a disaster. It was an adjustment. The forests adapted first. Trees evolved thicker roots to anchor themselves in soil softened by constant rain. Leaves developed waxy coatings to shed the moisture that fell almost daily. Plants in drier regions learned to conserve water, folding their leaves or growing smaller in stature. The Earth, as always, adapted to its own restlessness, but the patterns that emerged were new, and the balance that had once stretched evenly across continents began to fragment. The heat that had driven the expansion of life also drove instability. As warm air rose faster, it changed the pathways of wind. Atmospheric circulation reorganized itself. Monsoons, once confined to the tropics, reached further north and south. Equatorial rains grew heavier, while regions at mid-latitude saw unpredictable dry seasons. Even the poles, where warmth had brought forests, began to experience more variation, storms sweeping through regions that had once been calm. If you stood in one of those ancient polar forests then, you might have seen the sky darken without warning, clouds forming thick and fast in the warm, moist air. Thunder rolled across landscapes that had rarely heard it before. Rain would pour for hours, sometimes days, feeding rivers that overran their banks and carved new channels through the soil. Then, just as suddenly, the sky would clear, the air still thick but calm, the sunlight hazy and golden through lingering mist. Everywhere, weather was writing new geography. Floodplains expanded, reshaping coasts and deltas. Lakes formed and drained. Soil erosion increased, sending minerals and carbon into the sea. Those minerals helped feed marine life, providing nutrients that the warming oceans needed, but they also altered chemistry, accelerating the drawdown of carbon dioxide. In ways that no living thing could perceive, the planet's own instability was setting the stage for its eventual cooling. But that cooling was far in the future. In this moment, the world was alive with extremes. Heat waves lasted longer. Rain came in torrents. Lightning struck more often, igniting fires in the thick forests. These fires, though destructive, were part of a natural rhythm. They cleared underbrush, released nutrients, and opened space for new growth. The forests had evolved with this cycle, and in the warmth, fire became another form of renewal. The smell of smoke was not rare in that age. The air, rich with oxygen and heat, carried the faint memory of burning wherever the winds travelled. The continents, still shifting slowly on their tectonic plates, influenced this new weather as well. Mountains redirected air currents, creating rain shadows and dry basins. Oceans, warm to their depths, released vast amounts of vapour. The difference between land and sea temperatures drove winds of new strength and pattern. It was as if the planet had begun to experiment again with how to distribute its own energy. For the mammals and birds that filled the forests and plains, this variability demanded ingenuity. Some species adapted to cycles of abundance and scarcity. Fruit-eating animals learned to migrate between regions following the ripening of plants. Insect populations, driven by temperature and moisture, surged and crashed in rapid succession, forcing predators to adapt their diets. The rhythm of survival became less about constancy and more about timing. Those who could sense the change in air pressure or detect the faint signals of coming storms had an advantage. In the tropics, the warmth intensified convection, the upward movement of moist air that powers storms. Clouds built higher, reaching deeper into the atmosphere. Rainfall grew heavier. Lightning became more common. The skies turned dramatic, filled with towering cumulonimbus clouds that spanned horizons. Yet even in their ferocity, these systems were part of a cycle. They transferred heat away from the equator, carrying it toward the poles, helping to maintain the balance of the planet. The Earth's wild weather was not disorder for its own sake. It was an adjustment, a rebalancing act between regions of heat and regions of cooling potential. One of the more subtle effects of this period of volatile weather was its influence on evolution. Climate instability creates pressure, not constant enough to annihilate, but variable enough to reward flexibility. Species that could survive both flood and drought, both abundance and scarcity, flourished. Those bound too closely to narrow conditions struggled. In this way, the unpredictability of the climate accelerated adaptation. Life learned to be inventive. The fossil record from this era shows clear evidence of periodic droughts followed by floods. Sediment layers alternate between those formed in dry conditions and those deposited by heavy rainfall. River deltas expanded and contracted. Lakes filled, dried, and filled again. Each cycle left its mark, preserved for millions of years. What we see today as bands of colour in exposed cliffs were once the rhythms of a living, breathing planet adjusting to its own warmth. The animals of that age would have experienced this not as catastrophe, but as normality, The rains came and went. The forests burned and grew back. Rivers changed course, and the herds followed. The sky's moods were part of life's pattern. The climate of that time was not gentle, but it was consistent in its inconsistency. The same kind of restlessness that defines all natural systems once they've been pushed away from equilibrium. As the weather grew wilder, the atmosphere itself changed in texture. With more water vapour circulating, clouds became a constant presence. They reflected sunlight during the day and trapped heat at night, maintaining a humid warmth that never fully dissipated. In some regions, fog rolled in from the sea and lingered for days, creating conditions perfect for lush plant growth. The landscapes were vivid, alive with green, but never truly dry. Lightning-driven fires continued to shape those landscapes. Charcoal deposits in ancient soils mark their frequency. After each burn, grasses and shrubs returned quickly, feeding herbivores that thrived on the new shoots. The world was in constant renewal. Nothing stayed the same for long, but everything came back, adjusted slightly for the next cycle. It was a kind of balance within turbulence, a dynamic equilibrium that defined the middle of the Eocene. The oceans too mirrored the restlessness above. Warm surface waters fueled evaporation, feeding the atmosphere with moisture. Storms formed over open seas, growing vast and persistent before moving inland. Some scientists believe that hurricanes, or their ancient equivalents, may have been more frequent and perhaps even larger than those we know today. Their footprints are difficult to trace, but the sedimentary evidence, chaotic layers of storm deposits across coastal regions, suggests that the tropics pulsed with recurring tempests. These storms carried heat and nutrients across the globe. When they reached coastal forests, they deposited minerals from the sea, enriching the soil. The exchange between ocean and land intensified, each feeding the other's vitality. It was, in its own way, a planet working efficiently, even if it looked, from within, like disorder. The high latitudes, once calm and mild, began to experience the same volatility. Though still warm, they grew wetter and windier. The endless days of sunlight in summer fueled powerful convective storms. In winter, when the sun dipped below the horizon, the air cooled just enough to create dense fogs and long, misty twilights. The forests endured, but they learned to live with weather that was less predictable, more alive. This newfound turbulence had a side effect. It increased the rate at which carbon was cycled through the environment. Fires released carbon dioxide, but the regrowth that followed drew it back down. Heavy rainfall accelerated erosion, exposing fresh rock that reacted with the air to sequester carbon through chemical weathering. The balance of emission and absorption fluctuated wildly, but over long stretches of time it was leaning slowly toward removal. The Earth, through all this chaos, was beginning to correct its own fever. The process was far from linear. There were intervals of calm when the climate steadied again, followed by centuries of instability. The planet was learning how to redistribute the heat it had trapped. Weather became the mechanism of that redistribution, an invisible hand moving energy from one part of the globe to another. The result was a world of constant motion, clouds forming, rain falling, rivers reshaping, winds howling, all part of a single vast system in search of balance. For those who study these ancient climates, this period stands out not for catastrophe, but for energy. The Earth was vibrant, charged, alive with potential. The weather was wild, but it was not destruction. It was vitality. Every storm, every flood, every fire played a role in mixing the ingredients of life, spreading nutrients, and maintaining diversity. Without that chaos, evolution might have slowed. As the ages passed and the atmosphere gradually began to release its excess carbon, the intensity of these storms would ease. But before that slow calming came, the world experienced one of its most dynamic phases, a time when air and water worked together to rewrite the landscape, and while the skies were busy with thunder and rain, the oceans beneath them continued their quiet expansion. The warmth was still feeding the slow rise of sea levels, pushing the shoreline inward, reshaping continents one wave at a time. Land that had once been forest was sinking under the tide, and the mammals that had ruled the coasts were beginning to face a new kind of challenge, not from the air, but from the encroaching sea. The sea had been patient through all of it. While the air thickened and the forests spread and the storms learned new ways to travel, the ocean had simply continued its quiet expansion. Water moves slowly, but it never stops. As the world warmed, glaciers melted and thermal expansion took hold, pushing the boundaries of the ocean higher, inch by inch, decade by decade, until the outlines of continents began to blur. The sea was not invading in rage. It was arriving with inevitability, an ancient guest reclaiming old ground. In those warm ages, the sea level stood tens of meters higher than it does now. The coastlines we recognise today were buried beneath shallow sunlit waters. Plains that had once been home to forests and mammals became lagoons and estuaries. What had been distant inland turned to archipelagos. The world was not drowning in the dramatic sense we imagine. There was no single moment of submersion. Instead, it was a long, slow dinner, where the ocean simply helped itself to more of the table. This rise in sea level reshaped everything. It transformed ecosystems, created new habitats, and erased others. The coasts of that world were broad and complex, fringed with deltas, mangroves, and tidal forests. Rivers emptied into seas that reached far inland, creating brackish zones where fresh water met salt. Those boundaries, always rich with life, expanded across continents. Here, evolution worked with particular creativity. Fish adapted to variable salinity. Plants learned to anchor themselves in shifting sands and silt. Crustaceans, amphibians, and early marine mammals found endless opportunity in the overlap between land and sea. From a distance, these regions must have looked extraordinary. The air shimmered with humidity. Vast stretches of shallow water reflected the sky, dotted with islands of vegetation. Trees grew right out of the tide, their roots half submerged, their leaves reaching into a hazy atmosphere. The tides would have been stronger, the moon slightly closer in its orbit, the gravitational pull carving wide arcs of water along the coasts. Twice a day the ocean advanced and retreated, sculpting the edges of continents in patterns still faintly visible in the fossil record. For the mammals that had spread across the land, this changing shoreline offered both challenge and invitation. Food was abundant in the tidal zones: fish, shellfish, crustaceans and plants that grew in the nutrient-rich shallows. The early ancestors of whales, creatures that had once lived entirely on land, began to wade into this world. Over generations, they grew more at home in the water, their limbs reshaping for swimming, their lungs adapting to longer dives. The warmth of the global sea and the richness of the coasts made that transition possible. What began as foraging along the edge became a permanent migration into the ocean. The great lineage of marine mammals was born in these encroaching tides. The expansion of the sea also changed the chemistry of the world. As more land was submerged, sediments were reworked and deposited in new layers. Minerals from weathered rock mixed with marine sediments, creating thick bands of limestone and shale. These layers captured the story of the age, fossils of tropical plants and animals preserved in what are now high cliffs, far from any modern shore. Every stratum is a snapshot of that ancient coastline, where the sea advanced, paused, and withdrew over cycles lasting thousands of years. Inland, the changing sea level altered the flow of rivers. Drainage basins shifted, lakes merged or disappeared, and fertile floodplains transformed into shallow bays. The Earth's hydrological system was constantly redrawing its own map. Rain that once fed a forest might now fall on the open sea. The carbon and nutrients that rivers carried into the oceans fertilized vast blooms of plankton, which in turn absorbed carbon dioxide and sank to the seabed when they died. The same sea that had risen to cover the land was beginning slowly to help the planet cool. This interplay between warmth and water is one of the Earth's most intricate balancing acts. The ocean doesn't just respond to temperature, it regulates it. By spreading across more of the planet's surface, it absorbed additional heat and energy from the sun. That heat was distributed through currents, carried poleward, and radiated back into the atmosphere. The effect was stabilizing, though it came with consequences. The expanded seas moderated temperature swings, but they also transformed the shape of the continents forever. If you were to walk along one of those ancient shorelines, you would have found a landscape of transition. The ground underfoot would shift from firm soil to sand to soft mud, then to shallow water teeming with life. Shells would crunch beneath your steps. The smell of salt and decay would mix with the scent of vegetation. Small mammals might dart between mangrove roots, scavenging for crustaceans. Birds, ancestors of modern seabirds, would circle overhead, diving for fish. The boundary between land and ocean wasn't a line, it was a gradient, a living spectrum of earth becoming water. The plants of those coasts were remarkable in their resilience. They anchored themselves in shifting sediments, stabilizing the ground even as tides reshaped it. Their roots trapped silt and organic matter, building new land as quickly as the ocean eroded it away. These coastal forests became vital carbon sinks, storing the atmosphere's excess carbon in soil that remained waterlogged and oxygen poor. For millions of years, they helped balance the global cycle, one of the planet's quiet mechanisms for healing. But the ocean's expansion wasn't gentle everywhere. In some regions, the flooding outpaced adaptation. Valleys filled, ecosystems fragmented, and species that couldn't move fast enough vanished. Islands appeared and disappeared as sea levels fluctuated over centuries. The geography of the world became more fluid than ever before, changing not in sudden disasters, but in a slow, relentless motion. There are places on Earth today where the evidence of those ancient coastlines still lingers. In the rocks of Europe and North America, layers of marine sediments lie hundreds of meters above sea level, filled with fossils of tropical fish and shells. These are not accidents of imagination. They are remnants of that warm sea that came to dinner, that claimed vast parts of the continents as its own. In that era, the colour of the oceans was different too. With higher temperatures and more nutrients washing from land, the surface waters were often greener than blue, alive with plankton. Algal blooms covered vast areas, feeding the marine food web but sometimes consuming oxygen as they decayed, creating temporary dead zones. It was another reminder that abundance and scarcity are never far apart in nature. Too much of one thing always tips into the other. The warmth of the seas also affected the air above. Evaporation rates increased, fueling storms that swept across the coasts. Rain fell more often and more heavily, sometimes for days at a time. Thunder rolled across the lowlands. The boundary between ocean and sky blurred in mist and rain. From above, it might have looked as though the planet was wrapped in perpetual humidity. A greenhouse world indeed, its surface shimmering with water and light. And yet, even as the ocean expanded and the land retreated, the overall balance of the planet was inching toward recovery. The processes that draw carbon from the atmosphere, weathering of rocks, burial of organic matter, sedimentation, all accelerated in the presence of warmth and water. The more it rained, the more carbon was locked into minerals. The more the seas rose, the more they stored in their depths. The very mechanisms that had once amplified the heat were now beginning, slowly, to counteract it. Life, too, continued its adjustment. New species of fish appeared, specialized for shallow, warm seas. Mollusks evolved shells that could withstand changing salinity and acidity. Coral-like organisms spread across the tropical shelves, creating reefs in regions far from the equator. The mammals that had ventured into the water became faster, more graceful, their limbs reshaping into fins. Evolution was as relentless as the tides, responding to each shift with invention. The slow advance of the sea also changed the sound of the world. Waves reached farther inland, their rhythmic pulse a new presence in regions that had once known only wind and leaves. The ocean carried sound differently in that warm, dense air, a constant low hum that mingled with the calls of birds and the movement of animals. For the creatures living there, it was the background music of existence. What makes this time so striking is its balance of destruction and creation. The ocean's rise erased landscapes but gave birth to new ones. It drowned forests but created vast wetlands. It forced species to move but offered new spaces to fill. The planet was not suffering. It was experimenting, reorganizing itself around new conditions. The boundaries of habitability were redrawn, but life followed them effortlessly. Over the millennia, the sea's slow feast reached its peak. Shorelines stabilized, the warmth lingered, and the earth, though still hot, found a kind of equilibrium. The continents had been reshaped, ecosystems reinvented, and the carbon cycle was beginning to tilt toward cooling again. The ocean had eaten its fill, and the world rested in its new form, greener, wetter, and more connected than before. But nothing on Earth stays fixed for long. The same chemistry that allowed the ocean to rise would, over millions of years, begin to pull carbon from the air faster than it was replaced. Weathering would accelerate. Volcanoes would quiet. The balance would shift again, this time toward cooling. The warmth would fade gradually, and the ocean would begin its long, slow retreat. For now, though, in that moment of deep time, the sea had made itself at home. It lapped at the roots of forests, fed the rivers that carried its own salt, and turned the continents into mosaics of land and water. It wasn't an invasion. It was a return, a reminder that the edges of the earth have never been permanent, that every coastline is only temporary. And as the ocean settled into its new boundaries, the life that had adapted to its rise continued to evolve. From those coastal waters came new species that would define the next age of the planet, not only in the sea, but on land. Because the warmth, the instability, and the ever-changing boundaries had forced life to learn something vital: how to endure through motion. The world had become a place of travellers, of species in constant migration, of systems that never stood still. It was through this constant movement that resilience emerged. The Earth had proven, once again, that even in upheaval, balance is possible. The sea had come to dinner, and though it changed everything, it left behind a world ready for the next turn in the long rhythm of climate. The beginning of renewal, and the slow, steady path toward the forms of life that would one day inherit its story. In every era of upheaval, the Earth has always done the same thing. It has found a way to continue. The warmth that had stretched across oceans and forests, that had redrawn coastlines and flooded valleys, could have been an ending. For countless species it was. But for the world as a whole, it was only another turn in the cycle of transformation. The planet never stopped making life. Even as ecosystems shifted and old patterns vanished, new ones were already forming in their place. Change, for the Earth, is not a pause in life. It is life itself. The age that followed the Great Warming was one of quiet adaptation. The seas were still high, the air still heavy with moisture, but the frenzy of upheaval had begun to ease. The systems that had been thrown off balance were now stabilizing. Carbon was being drawn back into the rocks and oceans. The temperature was leveling off, and ecosystems were learning the rules of the new world. In the silence after so much motion, life began to specialize, refine, and settle into its new forms. The mammals, which had already conquered the land in diversity and number, became even more versatile. The small, generalized creatures of the earlier Eocene gave rise to lineages that explored every possible way of living. In the forests, primates grew more complex, their brains enlarging, their hands becoming more skillful, their social structures more elaborate. In open plains and floodplains, grazing animals adapted to tougher vegetation. Carnivores evolved sharper senses and more efficient hunting strategies. Bats learned to navigate the night sky with sound. Whales, once tentative shoreline dwellers, became fully aquatic, sleek and powerful, their new realm the open sea. The warmth that had once threatened life had now become the stage on which it flourished. Plants were evolving too. The forests that had covered the continents continued to expand and diversify. Flowering plants dominated, their intricate relationships with insects driving coevolution on a massive scale. Every colour, scent, and shape had a purpose: to attract, to protect, to survive. Pollinators thrived, and with them, the ecosystems became more tightly woven than ever before. The planet's surface, from canopy to forest floor, became a living machine of adaptation. But what makes this age remarkable is not just its abundance, it's the persistence that underlies it. Life had faced one of its most extreme global transformations, and instead of collapsing, it reorganized. Species that couldn't adapt gave way to those that could. New ecological networks formed, more flexible, more interconnected. Each extinction was followed by opportunity. The loss of one species made room for another. In this way, life didn't merely survive the heat, it became more intricate because of it. If you could see the Earth then, it would appear vibrant and whole again. The forests at the poles remained, though now slightly less tropical. The equatorial regions pulsed with growth. The oceans had recovered much of their oxygen, supporting complex webs of marine life. Coral-like organisms, having survived the acidification of the earlier ages, were rebuilding their reefs in new patterns. The great whales, descendants of land mammals that had embraced the ocean, were beginning their long migrations across the world's waters. They were the first true global travellers, moving between hemispheres, linking ecosystems separated by entire oceans. This global connectedness became one of the hallmarks of the age. The warm, stable climate created corridors for movement that spanned continents. Species spread easily, mixing genetic diversity on a planetary scale. The world, for a time, functioned as a single vast ecosystem. It was as if the planet had reached an equilibrium of openness, a living circulation of forms and genes that crossed every boundary. Beneath the surface of this balance, the same quiet processes that had always shaped the Earth continued. Volcanoes still erupted, though less frequently, feeding nutrients into the air and water. Mountains still rose, their fresh rock drawing carbon from the atmosphere through weathering. The oceans continued to act as a vast chemical reservoir, slowly absorbing the excess carbon that had once overheated the air. Each of these processes worked in harmony, not consciously, but inevitably. The system was finding its centre again. Even in recovery, however, the traces of the earlier chaos remained. Many of the species that had emerged during the warming bore the imprint of it in their physiology. Some mammals retained small body sizes, an evolutionary echo of the heat-stressed ancestors who had learned to survive in hot climates. Certain plants had evolved deep root systems and drought tolerance that remained even as rainfall stabilized. These were memories encoded in biology, the planet's living record of its own adaptation. There is a lesson hidden in that pattern. Every great shift in Earth's history has left behind a similar mark. When the planet cools, life becomes more compact, more energy efficient, conserving warmth. When it warms, life becomes expansive, curious, and restless. Each age leaves its influence on the DNA of the future. The resilience we see in life today, the ability to survive deserts, droughts, floods, and extremes, was built during times like these, when the world demanded flexibility as the price of existence. In the oceans, the recovery was slower but just as profound. The circulation that had once stalled was now fully renewed. Warm and cold waters mixed again, carrying oxygen to the depths. Plankton, the foundation of marine ecosystems, returned in full force, their population stabilizing. The chemistry of the sea began to shift toward balance. Coral reefs grew once more, and the ancestors of modern sharks and whales established themselves as the dominant predators. The entire marine biosphere from surface to seafloor had rebuilt itself. And yet, even as the planet found its balance, it was never static. The cycles continued. The Earth was already preparing for its next chapter, though it would take millions of years to unfold. The processes that draw down carbon never stop. With each century, a little more was locked into stone, a little more carried into the deep ocean. The warmth began its slow, barely perceptible decline. The forests would one day thin, the seas would one day retreat. But in this long middle act, the world was full of motion and life. The adaptability of species during this era shows a truth that often goes unnoticed. Stability is not what sustains life. Response does. The ability to change, to adjust, to find a new niche or strategy is what keeps ecosystems alive through upheaval. The mammals of this age embodied that principle perfectly. They were varied not just in form but in behaviour, in how they interacted with their environments. Some hunted, some grazed, some flew, some swam. They spread into every corner of the globe, not because the world was easy, but because it kept changing. One of the most fascinating consequences of this widespread adaptability was intelligence. In complex and shifting environments, awareness becomes valuable. The early primates that navigated the dense forests of the Eocene needed to remember where fruit trees grew, which routes were safe, and how to communicate with others. Their brains began to favour pattern recognition, problem solving, and social learning. These abilities would eventually define an entire branch of evolution. The mind itself, the capacity to learn, to anticipate, was, in many ways, the ultimate adaptation to a changing planet. Meanwhile, plants continued their silent transformation of the atmosphere. The forests of this era were more efficient at drawing down carbon than those of any time before. Root systems grew deeper, leaves more specialised. The cooperation between plants and fungi, the mycorrhizal networks that link roots beneath the soil, became more intricate. These underground systems helped stabilise ecosystems, sharing nutrients and water across entire forests. In a way, the planet's recovery was not just chemical, but communal. Life was rebuilding itself not as isolated species, but as interdependent networks. The world that emerged from the Great Warmth was therefore one of balance achieved through complexity. It was no longer a simple greenhouse of abundance. It was a web of relationships fine-tuned by millions of years of adjustment. Every creature depended on another. Every plant, every insect, every bird played a role in maintaining the flow of energy through the system. The resilience of that balance would endure for tens of millions of years, carrying the planet through its slow cooling and into the modern age. It's remarkable to think that all of this, the forests, the mammals, the diversity of life, was the result of a temperature change that began with just a few degrees. The same heat that had once threatened to suffocate the oceans had ultimately made the planet more alive. The Earth does not move in straight lines. It oscillates, weaving destruction and creation together in one continuous motion. When the warmth finally began to ease, the forests at the poles receded. Ice began to form again in small isolated patches. The cycles of seasonality grew stronger. Migration became a necessity once more. The animals followed the changing climates, just as their ancestors had followed the tides. Life never resists the planet's rhythm. It learns to dance to it. And in that dance, the blueprint for all future resilience was written. The ability to adapt to scarcity, to move with the seasons, to exploit both land and sea. These were the traits that would define life on Earth for millions of years to come. The recovery from the Great Warming was not a return to what had been before. It was the birth of something new, something more sophisticated. The Earth had proved again that it could heal itself, but not by undoing change, by evolving through it. The warmth had left its imprint in every gene, every ecosystem, every corner of the biosphere. It had reshaped the way life interacts with the planet itself. The relationship between atmosphere and organism, between chemistry and behaviour, had grown inseparable. Even now, traces of that ancient resilience remain in the DNA of living species. The plants that survive drought, the animals that migrate with precision, the microorganisms that thrive in heat or cold, all of them carry the legacy of that time when the world tested its limits and found a way forward. The Earth never truly recovered by returning to the past. It moved ahead, changed and more intricate than before. Life had learned once again how to breathe in rhythm with the planet, and that rhythm, the slow pulse of adaptation, would carry it through the cooling that was still to come. Because after every age of warmth comes the long sigh of return, when the world remembers the quietness of ice and the clarity of cold air. And as that long transition began, the signs of what had come before were left behind in stone and shell, in soil and fossil, in the chemical traces locked within polar layers. They would remain there, hidden and silent, until another time. Until the moment when creatures capable of asking questions would uncover them and wonder what it all meant. The warmth had lasted for millions of years, long enough for the planet to forget the meaning of cold. But the Earth never truly forgets anything. Deep beneath the forests, in sediments and buried soils, the slow arithmetic of balance continued. Rain fell on mountains, rivers carved valleys, and every drop of water that touched rock carried away a little carbon from the air. The oceans buried that carbon in their depths. The chemistry of the atmosphere began to lean, very slowly, toward coolness again. The planet was drawing in a long breath after its fever, and the memory of what had been would soon be locked away, not in books or words, but in ice. When the temperature began its descent, there was no announcement. The sun rose and set the same way. The trees still grew, the river still ran. But somewhere in the deep ocean, the cold current started to strengthen, and somewhere in the high latitudes, snow began to linger longer each year. The forest that had once reached the poles started to thin. Some species of trees could no longer handle the new rhythm of freeze and thaw. Grass began to take root in their place. Life felt the shift before the land did. Migration patterns changed. Animals began to move southward, following warmth that retreated step by step. The cooling was gentle at first. It took hundreds of thousands of years for permanent ice to return. But once it did, it became the new sculptor of the world. Mountains were ground down by glaciers, valleys filled with ice. Sea levels fell as water locked itself in frozen storage. The planet was rediscovering its balance through contrast. Warmth in some places, cold in others, seasons growing stronger, boundaries between climates re-emerging. In the layers of this new ice, the story of the earlier world was being written backward. Each snowfall trapped tiny bubbles of air. Each season left behind a trace of dust, pollen, or salt. Over time, these layers built up like pages in a book. The ice preserved what no other medium could: the atmosphere itself, the ratios of gases, the fingerprints of ancient temperatures, the signatures of volcanic eruptions. All were recorded molecule by molecule. The warmth that had once been everywhere now existed only as an echo, sealed beneath the surface of the poles. When modern scientists drill into those ice cores, they are not just sampling frozen water, they are reaching into that deep memory. Each metre of ice represents thousands of years. In some cores you can trace the faint line where the Great Warming ended, where the isotopes of carbon and oxygen begin to shift toward cooler values. It is a precise boundary, a chemical turning point, marking the Earth's slow recovery from its fever. What those trapped gases reveal is both familiar and haunting. The composition of the atmosphere during that ancient age, rich in carbon dioxide, heavy with water vapour, matches what we see returning today. The numbers are nearly the same. The difference, once again, is time. The ice doesn't lie, and it doesn't hurry. It tells of a planet that moves in cycles far beyond human scale. It records the pulse of warming and cooling, the rise and fall of greenhouse gases, the long oscillations that define geological time. Within those frozen layers, the memory of the last great 5-degree rise still lingers. Scientists can read how long it lasted, how quickly it rose, and how slowly it faded. The curve of that change is smooth, its descent gentle. Recovery took hundreds of thousands of years. There are no sharp edges in the data, only patience. That patience is one of the most humbling lessons the ice offers. The Earth does not rush to heal, because it does not consider its changes wounds. Each shift is simply another balance found, another form of stability. What feels like destruction to individual species, or to a single age, is just movement to the planet itself. The ice, silent and ancient, carries that truth in its depths, but it also carries details, intimate, almost microscopic ones. Tiny grains of pollen trapped in the layers tell of the forest that once reached the poles. The chemical ratios in those grains reveal what kind of trees grew, how much carbon they absorbed, how quickly they vanished. Dust particles trace the spreading of deserts as the world cooled. Sulfate layers mark volcanic eruptions that briefly interrupted the long decline in temperature. Even bacteria and spores still preserved in the ice tell stories of resilience. The planet's memory is not abstract, it's literal, it's physical, it's stored everywhere that water has frozen and refused to melt. As the ice expanded, the seas retreated, uncovering the coastal plains that the ocean had claimed during its feast. Rivers cut through the newly exposed ground, carrying minerals back to the ocean and fueling another round of sedimentation. The cycles continued, each connected to the last. The Earth was still busy rewriting itself, just in a slower hand. For life, this return of cold brought new pressures. The lush, equable world that had allowed forests from pole to pole began to break apart into regions again. Tropical belts remained, but temperate zones grew more distinct, and polar regions turned to tundra. The animals that had thrived in uniform warmth had to adjust to seasonality. Migration became essential. Hibernation evolved. Fur grew thicker, metabolisms adapted, and ecosystems reorganized around the rhythm of freeze and thaw. This shift gave rise to new evolutionary strategies: endurance, cooperation, and planning. The mammals that could anticipate the seasons fared best. Those who could store food, build shelters, or travel vast distances survived. Intelligence became a tool not of conquest, but of adaptation. The cold, it seems, encouraged foresight. The forests of the poles, though receding, did not vanish all at once. For long ages they persisted in pockets, refuges where warmth lingered. Fossils show that even as ice advanced, small groves of trees endured along coasts and valleys. Some species adapted to shorter growing seasons and lower light, becoming smaller and hardier. They waited out the cold, their roots deep in soil that still remembered warmth. Over time, the ice advanced further, covering the remains of those forests, burying the memory of their age beneath kilometers of frozen weight. That ice would move slowly, grinding down rock, carrying with it fragments of the world that came before, pieces of soil, pollen, and leaf. In that frozen mass, the Earth stored not just water, but history. When we cut into those cores today and release the ancient air trapped inside, it's as though the planet exhales its past. Each sample brings the soundless whisper of that greenhouse world, the humidity, the warmth, the carbon that once filled the atmosphere. It's a voice without tone, but it speaks clearly. The planet has been here before. The balance we live within now is not new. It's part of a repeating conversation between air, sea, and stone. There's something profoundly grounding in that realization. It reminds us that the climate we call normal is only a brief interlude in a much larger story. The ice preserves the evidence of that truth without judgment or urgency. It doesn't warn, it doesn't plead, it simply records. In those records, scientists have traced not only the Great Warming, but also the echoes of smaller events that followed, short pulses of heat, brief returns of tropical conditions and sudden cool spells. Each one corresponds to a shift in carbon, a rebalancing of the global system. The planet, it seems, is always in motion, oscillating between its states of fire and frost. When the first thin layers of ice formed after millions of years without it, the Earth crossed another threshold. Reflectivity increased again. Sunlight bounced away. The feedback loop that had once amplified warmth now amplified cold. Slowly, almost invisibly, the climate system flipped. What had been a greenhouse became a mirror. For the species alive then, these changes were just the world they knew. The cold advanced at a pace no generation could measure. A forest that took 1,000 years to vanish was still a forest to those who lived within it. The continuity of life never broke, even as its boundaries shifted. That's why the fossil record shows no moment of panic, only transition. The planet never stops moving from one form to another. It only pauses long enough for life to adapt. In the modern ice sheets, scientists can trace all of it: the ascent, the peak, the long descent, the stabilizing calm. The bubbles trapped within carry the ratios of ancient carbon and oxygen, the isotopic fingerprints that tell the story of a planet learning and unlearning heat. When they melt a section of that ancient ice and measure the air, they are breathing the same molecules that once drifted above Eocene forests, that once touched the leaves of trees growing in the Arctic sun. The continuity is literal, physical, intimate. It is one thing to know, in the abstract, that the Earth has changed. It is another to hold that change in your hand, to see it glinting in a vial of trapped air, to realise that the same carbon atoms are cycling again through the atmosphere today. The ice doesn't just record, it connects. It links the deep past to the present through chemistry. Those echoes in the ice are not warnings, though we often treat them as such. They are reminders, steady, factual, calm. They tell us that the planet is sensitive, responsive, alive in its own way, that a few degrees of difference can redraw its entire surface, that the systems we live within are ancient, tested and cyclical. They remind us that warmth and cold are not opposites, but partners in a slow dialogue that never ends. And as the world cooled into its next equilibrium, with ice reclaiming the poles and seasons sharpening their rhythm, the story of that earlier warmth did not vanish. It remained there, locked in the glaciers, in permafrost, in the chemical signatures of ocean sediment, waiting. Millions of years later, when creatures capable of thought began to study the planet that made them, they would drill into that ice and find themselves reflected in it. The same patterns of carbon rising and falling, the same sequence of warmth, reaction and recovery, the same 5 degrees that had once changed everything. The difference this time would not be the physics, or the chemistry, or even the scale of the response. It would be the speed. The echo that had been frozen for millions of years was beginning to sound again, not from the depths of geological time, but from our own age. And as the ice melts under a warming sky, the Earth's memory is no longer hidden. It is rising to the surface once more, to remind us that what we're seeing now is not a new story, only one we're living through again. The ice had held its silence for millions of years. Beneath its layers, the Earth's oldest memories slept: the heat, the carbon, the forests that once grew at the poles. For a long time, that silence remained unbroken. Then, in an instant too brief to be measured in geological terms, it stirred again. The balance that had taken eons to restore began to tilt. The carbon that had been locked in stone, in coal, in oil, in permafrost, began to return to the air. The planet's long, cool calm was ending, and the warmth was finding its way back. The fever had returned. At first, the signs were faint: a gradual rise in global temperature, a thinning of the polar ice, a shifting of seasons. But they were unmistakable. To those who study the planet's rhythms, the pattern looked familiar. It was the same curve the Earth had traced 56 million years earlier, the same sequence of cause and effect. Greenhouse gases rising, oceans warming, weather patterns changing. Only the timing was different. What had once taken thousands of years was now unfolding in centuries. The trigger this time was not volcanic or orbital. It came from within one species, clever enough to unlock the carbon of ancient ages but too short-lived to understand the timescale of consequence. When humanity began to burn coal and oil, it was tapping into the stored breath of the Eocene, the carbon laid down when the world had last been 5 degrees warmer. The forests, the plankton, the buried sediments, all the remnants of that long-ago abundance, became fuel. The warmth of that ancient sun, trapped in molecular bonds, was released again into the sky. The result, though measured in data, is something the planet already knows. The same gases, the same physics, the same feedbacks. Carbon dioxide thickens the air, infrared radiation lingers longer, oceans absorb heat, ice retreats, water vapour amplifies it all. The mechanics are simple, the implications vast. The Earth has begun another transition, one that mirrors its ancient past almost perfectly. The difference lies only in the pace. To understand how profound that difference is, imagine the last time the planet warmed by 5 degrees. It took roughly 10,000 years. Plants and animals had hundreds of generations to move, adapt, or evolve. Coastlines rose slowly enough for forests to migrate. Rainfall shifted at a pace that allowed species to find new niches. Today, that same change is projected within a few human lifetimes. Evolution, which once danced gracefully with the climate, can no longer keep time with it. The oceans have begun to respond first, as they always do. They've absorbed most of the excess heat, just as they did in the past, but this time they are warming faster than ever recorded. The upper layers are expanding, rising, and growing more acidic as they pull carbon dioxide from the atmosphere. The same chemistry that once dissolved shells in the Paleocene seas is repeating, only now it is measurable in decades. Coral reefs bleach, plankton populations shift, and the oxygen content of the deep water begins to fall. The oceans are once again struggling to breathe. On land, the warmth has started to redraw the boundaries of climate. Forests creep northward, deserts expand, rainfall patterns shift. Regions once mild face heat beyond memory. The balance between wet and dry, between fertile and barren, is changing faster than the soil beneath it can adjust. It is the same process that transformed the ancient world, but compressed, accelerated, intensified. This acceleration is what defines our moment. The Earth's systems are not foreign to these changes. They have done this before, but never with such speed. In the past, the carbon cycle had time to respond. Now, the feedback loops that once stabilized the planet are struggling to keep pace. Permafrost, thawing for the first time in thousands of years, releases methane, a potent greenhouse gas that amplifies the heat. Forests, stressed by drought and fire, switch from absorbing carbon to emitting it. The Earth's great carbon sinks are becoming sources. The patient regulators that once cooled the world are now joining the fever. For the first time, a species is watching it happen. The mammals that once adapted blindly to warming are now conscious of it, able to measure it, discuss it, and model its trajectory. Satellites track sea level rise. Instruments measure atmospheric composition with precision. Supercomputers simulate futures, each one an echo of possibilities written long ago in the ice. The difference is awareness. The question is what that awareness can change. It's easy to think of the current warming as something alien, something new and wholly our fault. But the truth is that it's part of a familiar rhythm. What makes it different is that we have accelerated the beat. The physics is ancient. The urgency is modern. The same sunlight, the same gases, the same laws of thermodynamics, all working faster as if someone has sped up the film of Earth's slow breathing. In the data, the resemblance to the Paleocene-Eocene thermal maximum is unmistakable. The isotopic fingerprint of carbon entering the atmosphere today matches that ancient pulse. Back then, the carbon came from volcanoes and seafloor methane. Now, it comes from combustion and deforestation. But chemically, it's the same material, released into the same sky. The Earth doesn't distinguish between origins. It responds only to quantity. Already, the signs of that response are visible. The polar regions are warming faster than anywhere else, just as before. Ice, once stable for millennia, melts into the sea. The Arctic Ocean, which was ice-free in summer 50 million years ago, may soon be so again. Forests burn in regions that once held permafrost. Storms draw their power from warmer waters, growing stronger and slower. Droughts deepen, and floods come with greater force. It is not apocalypse. It is physics. It is what the planet does when energy builds and balance tips. There's a strange symmetry in this repetition. The carbon that fueled modern civilization is the same carbon that built the Eocene world. The heat we are feeling now is the return of that buried sunlight. The forests that once grew in the Arctic are, in a sense, reappearing. Not through the same trees, but through the same temperatures. History on a planetary scale is circular. The Earth reuses its lessons. But this time, something unprecedented has entered the cycle. Awareness, responsibility, and the ability to measure consequence in real time. The creatures of the last warming could only adapt. We can anticipate. We can understand the chain of cause and effect that links a single ton of carbon to the chemistry of the air, to the behaviour of clouds, to the migration of species. It's an extraordinary gift, and an extraordinary weight. The ice cores that tell us of the past also show us the path we are now tracing. Their layers reveal the same rise in carbon dioxide that once triggered the 5-degree fever, but condensed into a single human epoch. If the past is any indication, the warming will not stop immediately when emissions cease. The Earth's systems have inertia. Heat lingers in the oceans, feedbacks take time to settle. The fever, once begun, runs its course. And yet the same record that shows us that inevitability also shows recovery. The planet always finds equilibrium again, even after its most extreme states. The question is not whether the Earth will survive. It will. It's whether the world that emerges will still be one we recognise. When the last great warming subsided, the planet was changed but thriving. New species had evolved. Ecosystems had adapted. The world was still alive, just rearranged. There's a certain comfort in that, and a certain warning. The Earth is resilient beyond comprehension, but it is indifferent to any particular arrangement of life. If pushed too quickly, it will reorganize without hesitation. The record in the ice shows no sentimentality, no hesitation, no pause. It simply moves toward balance. Today, the feedbacks that once took millennia are unfolding before our eyes. The same warm oceans that once fed abundance are now threatening coral reefs. The same expansion of forest that once absorbed carbon is now matched by fires that release it. The same sea level rise that once created new ecosystems is now erasing cities. The scale of transformation is similar, but this time it intersects with our own existence. For the first time, the species living through the warming has the ability to look backward and forward at once. We can see what happened last time the Earth heated by 5 degrees. We can see how long it took to recover. We can measure how much faster we're moving now. In that sense, our age is both a repetition and a reflection. The past is not repeating exactly. It is being condensed into a moment of decision. The fever is not vengeance or punishment. It's a reaction, a correction. The planet is doing what it has always done, balancing energy. But we are part of that balance now, both cause and observer. The warmth we've summoned will move through the same sequences as before. Ocean expansion, weather reorganization, migration, adaptation, stabilization. The only unknown is how we will fit into the outcome. In the end, the lesson of the ice is not despair, but perspective. The Earth has endured heat before, and it will again. The question is whether our civilization, built on coastlines, dependent on stable seasons defined by predictability, can move as fluidly as life once did. The mammals of the Eocene adapted because they had no choice. We have a choice, but also a deadline. The fever has returned, and with it the chance to understand what it means to live on a planet that breathes in cycles, to see ourselves not as separate from the system, but as part of its current state. The warmth is not the end of the world. It is the continuation of a rhythm as old as the atmosphere itself. The last time it happened, the Earth rebuilt itself in beauty and balance. Whether it does so again with us still here depends not on the planet, but on how well we remember its story. Because even now, as the ice melts and the oceans rise, the world beneath our feet is still capable of recovery. The forests still pull carbon from the air. The oceans still circulate, the rocks still weather, the balance still seeks itself. The fever will one day break, as it always has. What remains afterward will be different, not worse, not better, just new. And as the warmth deepens and the patterns of the world rearrange, the same quiet truth endures. The earth does not end, it transforms. The fever is only its way of remembering how to change. Even as the warmth settles in again, even as the seas rise and the seasons shift into patterns that no one alive has known before, the planet itself remains steady in one profound way. It remembers. Not in the way that we do, through stories or symbols or digital archives, but through its materials, its chemistry, its motion. Every change that has ever happened here is recorded somewhere. In ice, in stone, in the structure of cells, in the isotopes of air that drift through the sky. The Earth carries its memory not as a choice, but as a function of what it is. It keeps everything. If you could see that memory laid out all at once, it would not look like a straight line of history. It would look like a spiral. Each turn an echo of a previous one, each age connected to what came before. The same gases rise and fall, the same patterns of warmth and cold return, the same continents drift and collide, creating new mountains, new oceans, new possibilities. The world does not forget its earlier versions. It builds upon them. Every rock that forms, every organism that evolves, carries the trace of what preceded it. In the oldest rocks on the planet, there are chemical signatures of the first atmosphere. Faint traces of methane and carbon dioxide that tell us how the sun's warmth was once held close by primitive life. In younger rocks, there are bands of iron rusted by the first breath of oxygen released by photosynthetic organisms billions of years ago. In layers above those, the fossils of the first multicellular creatures, the imprints of their soft bodies preserved in sediments that were once sea floors. And higher still, the thick coal seams and oil deposits that record entire worlds of forests and plankton compressed into the planet's hidden vaults. Each of those layers is a memory. Each is an entry in the logbook of change. When the Earth warms, as it has before, those memories stir. The carbon stored in stone returns to the air. The water locked in ice re-enters the ocean. Energy moves through the system, awakening the cycles that have shaped the planet since the beginning. The processes that govern it, weathering, sedimentation, volcanism, photosynthesis, are the same ones that have always operated. The Earth doesn't need to invent new rules. It simply repeats the old ones, each time in a slightly different context. And through all of this repetition, life endures. It has done so through asteroid impacts, through mass extinctions, through ice ages that turned continents white, and heat waves that turned oceans green. Each time it adapts, diversifies, and reclaims the world in a new form. Even now, in the face of rapid change, that same tendency persists. Species are shifting ranges. Ecosystems are reorganizing. Some are failing, but others are emerging. Evolution has never been a story of stability. It's a story of persistence through instability. The memory of the planet is what allows this. The atmosphere, the ocean, the crust, and the biosphere are all connected through cycles that retain what has worked before. When carbon concentrations rise, chemical reactions accelerate to draw them down. When temperatures fall, those reactions slow, allowing warmth to build again. It's a form of homeostasis written into the planet's very chemistry. It doesn't ensure comfort for any one species, but it ensures continuity. The ice, as it melts, is releasing not just water, but history. Ancient air, trapped for hundreds of thousands of years, joins the modern atmosphere. Dust from distant deserts, pollen from vanished forests, bacteria from ecosystems long extinct. All of it re-enters circulation. The planet breathes its past back into the present. Even the carbon we release now was once part of a living world. The forests of the Eocene, the plankton of prehistoric seas. When we burn it, we are accelerating the planet's own cycle of remembrance. We are adding the voices of ancient climates to the chorus of the modern one. There's a strange poetry in that, though it isn't comforting. It means that every act of combustion, every rise in global temperature is also a reunion of sorts, the reunion of the present with its geological ancestors. The air outside your window carries atoms that once drifted through the lungs of creatures living in those polar forests. The rain that falls today has likely fallen countless times before, evaporated and condensed in endless repetition. Even the calcium in our bones was once dissolved in ancient seas. Nothing on this planet is new, everything is reassembled. To remember in the Earth sense is not to hold on to the past sentimentally, it's to integrate it into what comes next. The soil beneath us is a mixture of decay and renewal. The air we breathe is a blend of exhalations from millions of species. The water we drink has been part of every age, every extinction, every rebirth. The planet's memory is total, and it is participatory. We are part of it. In this moment, as the temperature climbs again and the glaciers retreat, the planet is not just reacting, it is recalling. The patterns we see in weather, in ocean circulation, in shifting ecosystems, all mirror those from millions of years ago. The feedbacks are the same, the sequence is the same, the memory is perfect, only the participants have changed. But even as the Earth revisits its old states, it also evolves. Each repetition is slightly different. The continents are in new positions. The sun shines a little brighter than it did 50 million years ago. The biosphere is composed of new lineages, new networks, new intelligence. The repetition is never exact. The planet remembers, but it also improvises. What stands out in all of this is that memory and change are not opposites. The Earth's capacity to transform is part of its memory. Every new equilibrium carries within it the record of the last. When the next ice age comes, the carbon we release today will still be written into the composition of the air. When future species evolve, their world will carry traces of ours, in the rocks, in the sediments, in the isotopic ratios of the ocean. We will be part of the geological record, not as an interruption, but as another line in the pattern. For those who study these things, the realization is humbling. It shifts perspective from fear to context. The planet is not fragile in the way we often imagine. It has endured cataclysms far greater than anything we can produce, but it is sensitive, exquisitely tuned to its own chemistry and energy. When that balance is disturbed, it responds with clarity. It remembers what equilibrium feels like, and it moves toward it no matter the cost. That movement toward balance is the essence of the Earth's memory. The cycles of carbon and water, the growth and decay of life, the advance and retreat of ice, all are ways of maintaining continuity through transformation. The fever that returns is part of the same process that will one day cool it. The recovery that follows will carry the imprint of what we do now. There's a deep continuity in that realization, one that ties every era together. The warmth of the Eocene, the chill of the ice ages, the temperate stability of the present. They are not separate worlds. They are chapters in the same story, written in different languages of climate and chemistry. The Earth does not start over. It accumulates. And when the next species, or civilization or consciousness arises to study the records we leave behind, It will find our traces just as we've found those of the past. It will read the carbon in the rocks, the plastics in the sediment, the metals in the soil. It will see the sudden spike in warmth, the rearrangement of ecosystems, the new patterns of extinction and adaptation. It will see in data and in fossils that once again the planet changed, and once again it continued. Perhaps that's the truest definition of a living planet. Not that it sustains life continuously, but that it never stops transforming. Its memory is not passive, it is active, creative, self-renewing. Each layer builds upon the last. Each age prepares the ground for the next. The Earth doesn't simply remember what it has been. It uses that memory to decide what it will become. As the warmth deepens and the patterns shift again, we are living inside that process. We are not apart from it. The air that thickens around us, the storms that grow stronger, the forests that migrate northward, these are not anomalies. They are the current expressions of the same ancient rhythm. The planet is remembering its capacity for heat, its flexibility, its resilience. It is doing what it has always done. And somewhere, far beneath our feet, in layers of soil and ice not yet formed, the traces of this moment are already being written. The dust from our cities, the carbon from our fires, the pollen from our crops, all of it is settling into the ground, joining the long archive of the planet's memory. One day it will harden into stone. One day it will be read again. The Earth does not forget and it does not stop. It turns, it breathes, it changes, and it remembers. What we call crisis, it calls transition. What we fear as loss, it records as motion. And when the balance returns, as it always does, the world that follows will carry the imprint of everything that came before. Our choices, our warmth, our moment. The planet will remember us as it remembers everything. And in that memory, life, in whatever form it takes next, will begin again.